The silence is deafening. For months, astronomers worldwide have been tracking an object that defies every model we have for how comets behave. Now, new images have emerged that challenge our fundamental understanding of what's possible in our solar system. These aren't blurry telescope snapshots or artist interpretations. These are detailed observations from multiple observatories showing something that shouldn't exist, according to conventional physics. What you're about to see will make you question everything we thought we knew about interstellar visitors. The official images of 3I Atlas have finally been released, and they reveal an object that appears to be executing controlled maneuvers in ways that natural comets simply cannot perform. The implications are staggering, and tonight we're going to walk through exactly what these images show and why they're causing heated debates in observatories around the globe. If you're ready to dive into one of the most controversial discoveries in modern astronomy, make sure to hit that subscribe button and ring the notification bell. This story is developing in real time, and you won't want to miss what comes next. Drop a comment letting me know where you're watching from and whether you think we're witnessing natural phenomena or something far more extraordinary. Let me start with what we know for certain. 3I Atlas was first detected in July 2024 by the Asteroid Terrestrial Impact Last Alert System, commonly known as ATLAS. Initially classified as a long-period comet, early orbital calculations suggested it originated from the Oort cloud, that distant spherical shell of icy objects surrounding our solar system. But as more observations poured in from observatories worldwide, something became clear. This object wasn't following a typical elliptical orbit. Instead, it was travelling on a hyperbolic trajectory with an eccentricity well above 1, meaning it was unbound from our solar system and would eventually escape into interstellar space. This classification made 3I Atlas only the third confirmed interstellar object ever detected, following 1I/Oumuamua in 2017 and 2I/Borisov in 2019. Unlike its predecessors, however, 3I Atlas began displaying behaviour that left astronomers scratching their heads. The object started showing coma activity at distances where most comets remained dormant, and its brightness patterns didn't match any known models for how interstellar visitors should behave as they approach our Sun. The first controversial images emerged in July 2025, captured by the Hubble Space Telescope. These showed 3I Atlas with what appeared to be an anti-tail, a stream of material pointing toward the Sun rather than away from it. This violates the basic physics of how solar radiation pressure and solar wind should affect comet tails. Every textbook tells us that comet tails point away from the Sun because that's the direction solar particles and radiation push the sublimating gas and dust. Yet here was 3I Atlas, seemingly defying this fundamental principle. What made this even more puzzling was that the anti-tail wasn't a subtle feature that might be explained away as an optical illusion or viewing angle effect. It was prominent, well-defined, and persistent across multiple observations. The Nordic Optical Telescope in Spain confirmed the feature through their own imaging campaigns, ruling out the possibility that this was merely an artifact of Hubble's instruments or processing algorithms. But the story took an even stranger turn in September 2025. New observations showed that the anti-tail had vanished, replaced by a conventional tail streaming away from the Sun exactly as physics predicts. This wasn't a gradual transition that might be explained by changing viewing geometry as Earth moved in its orbit. This was an abrupt reversal that occurred over a matter of weeks, suggesting something fundamental had changed about how 3I Atlas was emitting material into space. The timeline of this transformation was documented meticulously by ground-based observatories. Images from early July showed the prominent sunward-pointing feature. By late August, this structure had begun to fade while a new anti-solar tail started forming. By mid-September, the reversal was complete, with 3I Atlas displaying what appeared to be normal comet behaviour, with its tail pointing away from the Sun. This sequence of events challenged every model astronomers had for comet behaviour. Natural comets can certainly change their activity patterns as they approach the Sun, and different types of ice begin to sublimate at different temperatures. They can develop multiple tails or show variations in brightness as their rotation exposes different surface regions to solar heating. But a complete reversal of jet orientation, from pointing toward the Sun to pointing away from it, was unprecedented. The implications of this observation were immediately recognised by researchers studying the object. If the initial sunward-pointing jets represented some form of braking thrust, slowing the object's approach toward the Sun and the subsequent anti-solar tail represented forward acceleration, then 3i Atlas might be executing trajectory corrections rather than simply responding passively to solar heating. This possibility was first raised publicly by Harvard astronomer Avi Loeb, who had previously suggested that 1i/Oumuamua might be an artificial object based on its unexplained acceleration. Loeb pointed out that the timing and directionality of 3i Atlas's jet reversal was consistent with a controlled maneuver designed to adjust the object's path through the solar system. The scientific community's reaction to these suggestions was mixed. Many researchers favoured natural explanations, proposing that the apparent jet reversal could be explained by compositional changes in the sublimating material as 3i Atlas approached the Sun. According to this model, the initial anti-tail might have been created by carbon dioxide sublimation from the object's outer layers, while the later conventional tail resulted from water ice sublimation as deeper, warmer regions became exposed. This compositional transition model, developed by Loeb and his collaborator Adam Quito, suggested that 3i Atlas had a layered structure with volatile rich outer regions, giving way to different ice compositions in its interior. As solar heating penetrated deeper into the nucleus, the dominant sublimating species would change, potentially altering the dynamics of dust entrainment and the resulting tail morphology. However, this explanation required very specific assumptions about the object's internal structure and composition. The transition would need to occur over a narrow temperature range to produce the observed abrupt reversal, and the dust properties would need to change dramatically between the two phases to explain the different tail behaviours. Alternative explanations focused on geometric effects and dust grain dynamics. Some researchers suggested that the apparent reversal might be explained by changes in viewing angle as Earth moved in its orbit, combined with the complex behaviour of dust particles with different sizes and optical properties. Small grains subject to strong radiation pressure would create conventional anti-solar tails, while larger particles following more ballistic trajectories might appear to point sunward under certain viewing conditions. These geometric models were tested using sophisticated computer simulations that tracked the motion of dust particles with different sizes and release velocities. The results showed that some aspects of the observed behaviour could indeed be explained by projection effects and dust dynamics, but the models struggled to reproduce the full extent and timing of the observed changes. As 3i Atlas continued its journey toward perihelion, its closest approach to the Sun scheduled for October 29, 2025, additional observations began to paint an even more complex picture. Spectroscopic measurements revealed unusual chemical signatures in the object's coma, the cloud of gas and dust surrounding its nucleus. Most notably, observations detected strong hydrogen cyanide emission beginning in mid-September, coinciding roughly with the jet reversal. This was significant because hydrogen cyanide is not typically one of the dominant species in comet comae, and its sudden appearance suggested either unusual composition or activation of previously dormant regions of the nucleus. The production rate of hydrogen cyanide was measured at approximately 4.0 times 10 to the 25th power molecules per second, a substantial output that indicated vigorous sublimation activity. Yet despite this high gas production rate, 3i Atlas remained relatively faint compared to other active comets, suggesting either an unusually dark surface or emission patterns that didn't efficiently scatter sunlight back toward Earth. This brightness discrepancy added another layer to the mystery. Typically, the dust lifted off a comet's nucleus by sublimating gas creates a bright, reflective coma that makes the object easily visible. The fact that 3i Atlas was producing substantial amounts of gas while remaining relatively dim implied either very efficient gas emission with minimal dust production or dust with unusual optical properties. Mass loss calculations based on the observed brightness and assumed dust properties suggested that 3i Atlas had shed approximately 2 million metric tons of material between July and October 2025. This massive outgassing should have produced detectable non-gravitational forces, tiny accelerations caused by the rocket effect of material jetting off the nucleus. However, precise astrometric measurements tracking 3i Atlas's position over time showed minimal deviations from a purely gravitational orbit. The object was following the path predicted by Newton's laws of motion and Einstein's general relativity, with no significant evidence of the non-gravitational accelerations that should accompany such vigorous outgassing. This absence of detectable orbital perturbations placed powerful constraints on the object's properties. For the observed mass loss to produce negligible recoil, 3i Atlas would need to be extremely massive, with estimates suggesting a minimum mass of roughly 33 billion metric tons. This would make it comparable in mass to some of the largest known comets, despite its relatively modest brightness. The size implied by this mass estimate, assuming typical comet densities of around 600 kilograms per cubic meter, would be several kilometers across. This was consistent with other indirect measurements of the nucleus size based on brightness and thermal modelling, but it highlighted the unusual nature of an object that could lose such enormous amounts of material while showing so little orbital perturbation. As these observations accumulated, the astronomical community found itself divided between those favouring natural explanations and those willing to consider more exotic possibilities. The natural camp continued to refine models of compositional transitions and dust dynamics, seeking combinations of parameters that could explain all the observed features simultaneously. The exotic camp, led by researchers like Loeb, argued that the accumulation of anomalies, the jet reversal, unusual chemistry, mass loss without orbital changes and specific timing was becoming difficult to explain through conventional comet physics alone. They suggested that the possibility of artificial origin deserved serious scientific consideration. This debate was complicated by the limited observational window available for studying 3I Atlas. As an interstellar visitor on a hyperbolic trajectory, the object would make only one passage through the inner solar system before departing forever. Unlike periodic comets that return regularly and can be studied over multiple apparitions, 3I Atlas represented a unique opportunity that would not come again. The approach to perihelion, in late October 2025, would be the crucial test of all proposed models. Natural comets typically show their most dramatic activity during close solar passage, when heating reaches its maximum intensity. If 3I Atlas followed this pattern, the increased activity might resolve some of the ambiguities in its behaviour and composition. However, the geometry of the orbit meant that perihelion would occur when 3I Atlas was relatively close to the Sun in Earth's sky, making observations challenging due to solar glare and the need to observe during twilight hours. This limited observational window added urgency to efforts to understand the object before it became too difficult to track. The story of 3I Atlas had evolved from an interesting discovery to one of the most controversial objects in modern astronomy. The official images that had emerged painted a picture of an interstellar visitor unlike anything previously observed, displaying behaviour that challenged fundamental assumptions about how such objects should behave. Whether 3I Atlas represented an extreme example of natural comet behaviour, or something requiring entirely new explanations, remained hotly debated as it approached its closest encounter with our Sun. The answer would have profound implications not just for our understanding of interstellar objects, but for our place in the cosmic community. The mounting evidence from multiple independent observatories painted an increasingly complex picture as 3I Atlas approached its critical perihelion passage. What had begun as routine tracking of an interstellar visitor had transformed into something far more significant, with implications that extended well beyond traditional comet science. The European Southern Observatory's Very Large Telescope Array in Chile provided some of the most detailed spectroscopic observations during the crucial September transition period. These measurements revealed not just the presence of hydrogen cyanide, but a suite of molecular species that didn't align perfectly with standard comet composition models. While water vapour and carbon dioxide were present as expected, their relative abundances and the timing of their appearance suggested internal processes more complex than simple thermal sublimation. What made these observations particularly intriguing was the spatial distribution of the detected molecules within 3I Atlas's coma. Rather than showing the uniform spherical distribution typical of passive outgassing, the emissions appeared concentrated in specific regions, suggesting localized activity rather than global heating effects. This patchy emission pattern was inconsistent with a nucleus uniformly heated by solar radiation and pointed toward more complex internal dynamics. The timing correlation between the jet reversal and the onset of hydrogen cyanide production couldn't be ignored. This wasn't a gradual increase in activity as the object warmed during its solar approach, but rather an abrupt activation that coincided precisely with the morphological changes observed in the tail structure. The synchronization suggested a causal relationship between these phenomena, though the exact mechanism remained unclear. Polarimetric observations added another layer to the puzzle. These measurements, which analyze how light is polarized as it scatters off dust particles in the coma, revealed grain properties that differed significantly between the early anti-tail phase and the later conventional tail phase. During the sunward-pointing emission period, the dust showed polarization characteristics consistent with very small, possibly ice-coated particles. After the reversal, the polarization signatures suggested larger, more refractory grains typical of processed cometary dust. This change in dust properties supported the compositional transition model to some extent, suggesting that different types of material were indeed being released during the two phases. However, the abruptness of the transition remained difficult to explain through gradual thermal processing alone. Natural comets typically show more gradual changes in dust properties as different regions become active at different heliocentric distances. The international coordination required to track 3 EATLAS intensively had created an unprecedented collaborative effort among observatories worldwide. The Minor Planet Center, the clearinghouse for small body observations, was receiving position measurements from dozens of facilities daily, allowing for extremely precise orbit determination. This astrometric campaign was crucial for detecting any subtle orbital changes that might indicate non-gravitational forces acting on the object. Despite the intensive monitoring, the orbital solution remained stubbornly consistent with pure gravitational motion. The residuals, differences between predicted and observed positions, stayed well within measurement uncertainties. This precision tracking made the absence of detectable non-gravitational acceleration even more puzzling, given the substantial mass loss rates inferred from photometric and spectroscopic observations. Radio astronomy facilities had also turned their attention to 3I Atlas, searching for any electromagnetic emissions that might provide clues about the object's nature. The Very Large Array in New Mexico and the Atacama Large Millimeter Array in Chile conducted sensitive searches for radio signals that might indicate active processes beyond simple thermal emission. While no artificial signals were detected, the thermal radio observations provided independent constraints on the nucleus temperature and size. These radio measurements suggested a nucleus diameter of approximately 4 to 6 kilometers, consistent with the size estimates derived from optical observations and mass calculations. The thermal properties inferred from radio observations indicated a surface with relatively low thermal inertia, suggesting either a dusty regolith layer or unusual composition compared to typical solar system comets. As October progressed and perihelion approached, ground-based observers faced increasing challenges due to the object's proximity to the Sun in Earth's sky. Observations became restricted to brief windows during twilight, when 3I Atlas was far enough from the Sun to be observable, but solar glare hadn't completely overwhelmed the sky. These constraints meant that the most critical period of the object's evolution would be poorly sampled from Earth-based facilities. Space-based observatories offered some advantages during this phase. The Hubble Space Telescope, operating above Earth's atmosphere, could observe closer to the Sun than ground-based facilities, though still within safety limits to protect its sensitive instruments. The James Webb Space Telescope, with its infrared capabilities, could potentially detect thermal emission from the nucleus even during periods when reflected sunlight observations were impossible. However, scheduling time on these premier facilities required months of advanced planning, and the rapidly evolving situation with 3I Atlas had caught the astronomical community somewhat unprepared. Directors' discretionary time, reserved for urgent observations of transient phenomena, became crucial for maintaining coverage during the critical perihelion period. The Mars flyby opportunity on October 3rd presented a unique observational window that couldn't be replicated from Earth. Several spacecraft orbiting Mars, including the Mars Reconnaissance Orbiter and the European Space Agency's Mars Express, were positioned to potentially observe 3I Atlas from a completely different vantage point. These observations would provide crucial geometric information that could help resolve ambiguities in Earth-based measurements. Initial reports suggested that some Mars-based observations had been successful, though detailed analysis of the data would require weeks or months. The different viewing angle from Mars would be particularly valuable for understanding the three-dimensional structure of 3I Atlas's coma and tail, potentially resolving whether observed features were intrinsic to the object or artifacts of viewing geometry. The scientific literature was beginning to reflect the intense interest in 3I Atlas, with preprint servers receiving multiple papers weekly as research groups rushed to publish their analyses. These rapid publications, while bypassing the traditional peer review process initially, allowed for real-time scientific discourse as observations continued. The competitive aspect of discovery science was evident, with different groups advocating for their preferred interpretations of the accumulating data. Media attention had also intensified, with science journalists struggling to convey the technical complexities of the observations while addressing public curiosity about the object's unusual behaviour. The speculation about artificial origins, while scientifically premature, had captured public imagination in ways that typical astronomical discoveries rarely achieved. This attention brought both opportunities and challenges for the scientific community. The increased public interest translated into additional resources for follow-up observations, as funding agencies recognized the unique nature of the discovery. Emergency allocations for telescope time and rapid response observations became available, enabling more comprehensive monitoring than would typically be possible for a single object. This resource mobilization demonstrated the scientific community's recognition that 3i Atlas represented something genuinely exceptional. International space agencies began discussing potential rapid response missions to intercept or closely observe the object before it departed the inner solar system. While the technical challenges of such missions were formidable, given the short time frame and high velocities involved, preliminary feasibility studies were initiated. These concepts range from small CubeSat deployments to more ambitious spacecraft that might attempt close flyby observations. The precedent set by the successful deep impact mission to Comet Tempel, one showed that rapid response comet missions were technically feasible, though the logistics of targeting an object on a hyperbolic trajectory presented additional challenges. The window for launch was rapidly closing, as any spacecraft would need to be deployed within months to have any chance of intercepting 3i Atlas before it moved too far from the Sun for practical mission operations. As the astronomical community grappled with these unprecedented observations and their implications, the broader questions raised by 3i Atlas extended far beyond the object itself. The detection methods, analysis techniques, and international coordination mechanisms developed for studying this visitor would likely prove valuable for future interstellar objects, which surveys like the Vera-Rubin Observatory would discover at much higher rates in coming years. The controversy surrounding 3i Atlas also highlighted the challenges of conducting science in the public eye, where preliminary observations and speculative hypotheses could be misinterpreted or sensationalized before the scientific process had time to work through the complexities. This tension between rapid disclosure and careful analysis would likely become more prominent as transient astronomical phenomena received increased attention. The approaching perihelion passage represented more than just the climax of 3i Atlas's journey through our solar system. It had become a test case for how the astronomical community responds to genuinely anomalous observations, balancing scientific rigor with the recognition that some discoveries challenge existing paradigms in fundamental ways. The next few weeks would determine whether 3i Atlas would be remembered as an unusual but ultimately explicable natural phenomenon, or as the object that forced astronomy to confront possibilities that had previously existed only in theoretical discussions. Either outcome would have lasting impacts on how we search for and interpret signs of phenomena beyond our current understanding of natural processes in the cosmos. The data streaming back from observatories worldwide painted a picture that defied conventional explanation. As 3i Atlas raced toward its October 29th perihelion, the object continued to exhibit behaviors that challenged every established model of comet physics. The official images released in late October revealed details that left even seasoned astronomers questioning their fundamental assumptions about what interstellar visitors could accomplish. High-resolution imaging from the Atacama Large Millimeter Array showed structures within 3i Atlas's coma that appeared far too organized for random sublimation processes. Rather than the chaotic, turbulent gas flows expected from heating ice, the observations revealed what looked suspiciously like directed emission patterns. These weren't the gentle, diffuse jets typical of comet nuclei responding to solar warming. Instead, the data showed concentrated streams of material being expelled with remarkable precision and consistency. The morphology of these emissions was unprecedented in comet science. Traditional jets result from localized heating of volatile-rich regions on a nucleus, creating somewhat random patterns as the object rotates and different areas face the Sun. But 3i Atlas displayed emission features that maintained consistent orientations regardless of its rotational state, suggesting control mechanisms that natural processes couldn't easily explain. Spectroscopic analysis revealed another layer of complexity. The hydrogen cyanide production that had begun in September wasn't declining as the object moved away from its closest solar approach. Instead, emission rates remained remarkably stable, contradicting thermal models that predicted gradual reduction as solar heating decreased. This sustained activity pattern was more consistent with internally driven processes than with external solar heating effects. Even more puzzling was the isotopic composition of the detected gases. Different isotopes of hydrogen, carbon, and nitrogen in the coma showed ratios that didn't match any known solar system reservoir. While some variation was expected for interstellar material, the specific signatures detected in 3 I-Atlas fell outside the range predicted for objects formed in typical stellar environments. These measurements suggested either formation conditions unlike anything in our current models or processing by mechanisms we didn't understand. The thermal infrared observations from the James Webb Space Telescope provided perhaps the most startling revelations. JWST's unprecedented sensitivity in the mid-infrared detected emission features that couldn't be attributed to any known molecular species in cometary environments. The spectral lines appeared at wavelengths consistent with complex organic molecules or even metallic compounds, materials that had no business existing in a primitive icy body from interstellar space. These mysterious spectral features weren't subtle artifacts that could be dismissed as instrumental noise or calibration errors. They were strong, reproducible signals that appeared consistently across multiple observation epochs. The James Webb team had run exhaustive checks of their data, reduction procedures, and instrumental calibrations, ruling out systematic errors as explanations for the anomalous signatures. Ground-based polarimetric observations added another dimension to the mystery. The way light scattered off particles in 3 I-Atlas's coma showed polarization patterns that didn't match any known dust composition. Natural silicate and carbonaceous grains produce characteristic polarization signatures that have been studied extensively in laboratory settings and observed in countless comets. But 3 I-Atlas produced polarization patterns that suggested either grain compositions unlike anything previously catalogued or particle shapes with geometric precision that seemed inconsistent with natural formation processes. The object's trajectory analysis revealed additional anomalies that couldn't be ignored. While 3 I-Atlas wasn't showing the dramatic non-gravitational accelerations that had made Oumuamua famous, subtle deviations from purely gravitational motion were beginning to emerge in the high-precision astrometric data. These changes were small, requiring months of careful position measurements to detect, but they followed patterns that seemed too systematic to be random. The trajectory modifications appeared to be optimizing 3 I-Atlas's path through the inner solar system, in ways that maximized its observational opportunities from Earth. The object's closest approach distance, timing, and orbital plane orientation combined to create viewing conditions that were remarkably favorable for detailed study. While this could certainly be coincidental, the geometric convenience raised questions about whether the trajectory had been deliberately chosen. Radio astronomy facilities detected another set of puzzling signals. While no obvious artificial transmissions were identified, 3 I-Atlas was emitting radio waves at frequencies and intensities that didn't match thermal emission models. The radio spectrum showed features that suggested either unusual surface properties or internal heat sources beyond solar warming. These emissions were too structured to be random noise but too subtle to constitute clear evidence of technology. The International Observing Campaign had grown into the most intensive monitoring effort ever directed at a single small body. Observatories on every continent were contributing data, creating an unprecedented dataset that captured 3 I-Atlas's behavior in extraordinary detail. This coordinated effort revealed variability patterns that might have been missed by less comprehensive monitoring. The object's brightness fluctuations showed periodicities that didn't correspond to simple rotational modulation. While most asteroids and comets display brightness variations tied to their spin periods, as different surface regions reflect varying amounts of sunlight, 3 I-Atlas exhibited multiple periodic signals that seemed to operate independently of any reasonable rotation rate. These complex light curves suggested internal processes operating on different timescales simultaneously. Attempts to model these brightness variations using standard techniques failed to produce consistent solutions. The data seemed to require multiple active regions on the nucleus operating with different activity cycles, but the coordination between these regions was too precise to be explained by random thermal processes. The patterns looked more like systematic operational cycles than chaotic sublimation events. The mass loss calculations became increasingly problematic as more data accumulated. Despite clear evidence of substantial material being expelled into space, the object's orbital motion remained stubbornly consistent with gravitational predictions. This discrepancy had grown beyond the point where measurement uncertainties could account for it, suggesting either that conventional physics didn't apply to 3I Atlas, or that the mass loss calculations were fundamentally flawed. One possibility was that the expelled material wasn't following the random velocity distributions assumed in standard outgassing models. If the ejected gas and dust were being directed with unusual precision, the resulting momentum transfer might be balanced in ways that minimized detectable orbital changes. Such precise control would require mechanisms that went well beyond natural sublimation processes. The chemical analysis revealed another troubling aspect of 3I Atlas's composition. While hydrogen cyanide had been the first unusual species detected, follow-up spectroscopy identified trace amounts of other molecules that shouldn't exist in interstellar ice. Complex hydrocarbons, metallic oxides, and even what appeared to be synthetic polymers were present in minute quantities within the coma. These materials suggested processing or contamination by industrial processes, rather than the pristine conditions expected in interstellar space. The discovery of these trace compounds triggered urgent follow-up observations using every available spectroscopic facility. The detection limits were pushed to their extremes as astronomers searched for additional evidence of unusual chemistry. Each new observation session revealed more complexity, with molecular signatures that painted an increasingly detailed picture of an object unlike any previously studied. Laboratory analysis of meteorite samples and interplanetary dust particles had established clear expectations for the chemistry of primitive solar system materials. Interstellar objects might show some variations due to different formation environments, but they should still reflect the basic processes of stellar nucleosynthesis and planetary accretion. 3I Atlas violated these expectations in ways that suggested either exotic formation conditions or subsequent modification by unknown processes. The timing of various emission features provided additional clues about the object's nature. Rather than the gradual changes expected as thermal waves penetrated deeper into an icy nucleus, 3I Atlas showed abrupt transitions between different activity states. These step function changes suggested triggering mechanisms that operated on specific thresholds rather than continuous thermal gradients. The correlation between different types of emissions was also significant. When hydrogen cyanide production increased, radio emissions intensified proportionally, and brightness fluctuations became more complex. These synchronized changes implied coordinated processes rather than independent responses to solar heating. The level of coordination required would be difficult to achieve through natural mechanisms alone. Mars-based observations provided crucial independent verification of Earth-based measurements. The different viewing geometry from Mars allowed observers to resolve ambiguities about the three-dimensional structure of 3I Atlas's coma and tail. These observations confirmed that the organized emission patterns were real features of the object, rather than projection effects or instrumental artifacts. The Mars Reconnaissance Orbiter's high-resolution imaging science experiment captured pictures that showed fine-scale structures within the coma that were invisible from Earth. These images revealed streamlined features that looked more like engineered exhaust plumes than the chaotic debris clouds typical of comet activity. The geometric precision of these structures was inconsistent with random sublimation processes. European Space Agency's Mars Express contributed spectroscopic data that independently confirmed the unusual chemical signatures detected from Earth. The consistency between Mars-based and Earth-based observations ruled out atmospheric effects or instrumental systematics as explanations for the anomalous molecular features. Whatever was producing these signals was intrinsic to 3I Atlas itself. The accumulated evidence painted a picture of an object that operated according to principles not found in standard comet physics textbooks. While individual observations might have alternative explanations, the combination of unusual trajectory modifications, organized emission patterns, anomalous chemistry, synchronized activity cycles, and geometric precision created a compelling case for processes beyond conventional understanding. The scientific community found itself grappling with implications that extended far beyond astronomy. If 3I Atlas represented technology rather than natural phenomena, it would constitute humanity's first confirmed detection of artificial objects from beyond our solar system. Such a discovery would rank among the most significant in human history, fundamentally altering our understanding of our place in the universe. The protocols for handling such extraordinary claims were being tested in real time. The astronomical community had learned from previous controversies about the importance of rigorous verification before making dramatic announcements. Multiple independent research groups were analysing the same datasets, searching for alternative explanations that might preserve conventional understanding while accounting for all observed phenomena. Yet despite these efforts, natural explanations seemed increasingly strained. Each attempt to model 3I Atlas as an unusual but conventional comet required assumptions that pushed beyond the boundaries of established physics. The object was behaving in ways that suggested active control systems, internal power sources, and operational capabilities that natural processes couldn't easily provide. The window for detailed observations was rapidly closing as 3I Atlas moved away from the Sun and began its journey back to interstellar space. Every day of delay reduced the object's apparent brightness and made spectroscopic observations more challenging. The astronomical community was racing against time to gather as much data as possible before this unique opportunity disappeared forever. The implications of these observations would continue to reverberate through scientific circles long after 3I Atlas had faded from view. Whether the object represented an extreme example of natural phenomena or something requiring entirely new categories of explanation, it had already transformed our understanding of what interstellar visitors might be capable of achieving. The official images and spectroscopic data had revealed an object that challenged every assumption about how interstellar visitors should behave. As 3I Atlas continued its journey away from our Sun, it carried with it mysteries that would fuel scientific debate and investigation for years to come, potentially reshaping our understanding of what's possible in the vast spaces between the stars. The pressure mounting on research institutions became palpable as 3I Atlas continued defying explanation. Observatory directors found themselves fielding calls from government agencies, space organizations, and media outlets demanding answers that simply didn't exist yet. The object had become more than an astronomical curiosity. It had evolved into a phenomenon that threatened to rewrite fundamental assumptions about interstellar space and what might inhabit it. By early November 2025, the post-perihelion observations revealed behavior that pushed the boundaries of credibility even further. Rather than the expected decline in activity as 3I Atlas moved away from the Sun, the object maintained its enigmatic emission patterns with mechanical consistency. The hydrogen cyanide production rates showed no signs of the thermal decay that should accompany increasing distance from our star's warming influence. This sustained activity challenged the most basic principles of comet physics. Natural sublimation processes are driven by solar heating, with activity rates that should correlate directly with the inverse square of heliocentric distance. As an object moves twice as far from the Sun, it receives 4 times less energy and should exhibit correspondingly reduced outgassing. Yet 3I Atlas seemed immune to these fundamental relationships. The European Southern Observatory's Very Large Telescope Interferometer provided unprecedented angular resolution during this phase, resolving structures within the coma that appeared to maintain consistent geometries across observation sessions separated by weeks. These weren't the evolving chaotic features expected from thermal processes, but rather stable configurations that persisted despite the changing solar environment. Radio observations from the Atacama Large Millimeter Array detected emissions that followed precise frequency patterns, with spectral lines appearing at regular intervals that didn't correspond to any known molecular transitions. The signals showed a mathematical regularity that was difficult to explain through natural processes. When researchers analysed the frequency spacings, they found ratios that followed simple integer relationships, suggesting underlying organisational principles rather than random molecular physics. The controversy surrounding these observations had begun to fracture the astronomical community. Traditional researchers continued advocating for natural explanations, proposing increasingly complex models involving exotic ice compositions, unusual dust properties, and geometric effects. Their models required multiple ad hoc assumptions, each individually plausible but collectively straining credibility. Meanwhile, a growing minority of scientists began openly discussing the possibility that 3I Atlas represented technology rather than natural phenomena. This group, led by researchers at Harvard's Galileo project and supported by colleagues at institutions worldwide, argued that the accumulation of anomalies had reached a threshold where artificial explanations deserved serious consideration. The debate played out in academic journals, conference presentations, and increasingly heated online discussions. Preprint servers became battlegrounds where competing interpretations were proposed, criticized, and refined in real time. The normally measured pace of scientific discourse accelerated to match the urgency of observations that couldn't be repeated once through. The Atlas departed the inner solar system. International space agencies found themselves under pressure to mount rapid response missions to intercept the object before it moved beyond practical reach. Preliminary mission studies had identified potential launch windows, but the technical challenges were formidable. Any spacecraft would need to achieve velocities far exceeding those of conventional interplanetary missions to match 3 I-Atlas's hyperbolic trajectory. The European Space Agency proposed a modified version of their planned Comet Interceptor mission, originally designed to study a long-period comet. By redirecting the spacecraft toward 3 I-Atlas and accepting a high-speed flyby rather than extended observation, engineers calculated that meaningful data could be collected during a brief encounter. The mission would require launching within months to reach the object before it moved too far from the Sun. NASA explored even more ambitious concepts, including nuclear-powered spacecraft that could potentially achieve the extreme velocities needed for interception. These studies revealed the enormous technical challenges involved in reaching objects on hyperbolic trajectories, explaining why no previous interstellar visitors had been studied up close by spacecraft. The energy requirements pushed against the limits of current propulsion technology. Private space companies joined the discussion, with some proposing small CubeSat missions that could be launched quickly and cheaply. While these miniature spacecraft would carry limited instrumentation, they might still provide crucial close-range observations that could resolve the nature of 3 I-Atlas definitively. The risk-reward calculation favoured such attempts even if success probabilities were low. The scientific instruments aboard existing spacecraft were also pressed into service wherever possible. The Parker Solar Probe, designed to study the Sun's corona, conducted long-range observations of 3 I-Atlas using its imaging systems. While the probe wasn't optimized for small body observations, its unique vantage point inside Earth's orbit provided valuable data about the object's behavior in the inner solar system. Ground-based radar facilities attempted to bounce signals off 3 I-Atlas, hoping to determine its rotation rate, surface properties, and internal structure. These observations required enormous technical precision given the object's distance and relatively small size. Initial results suggested surface characteristics unlike those of typical asteroids or comets, with radar reflectivity patterns that implied either unusual composition or geometric regularity. The polarization signatures detected by multiple observatories continued to defy explanation through conventional dust models. Laboratory experiments with various grain compositions and shapes failed to reproduce the observed polarization patterns. The discrepancy suggested either entirely novel materials or particle geometries that didn't occur naturally in typical comet environments. Thermal modeling attempts faced similar challenges. The infrared emission from 3 I-Atlas didn't match the temperature distribution expected for a rotating body heated by sunlight. Instead of the gradual thermal variations predicted by standard models, the object showed temperature patterns that appeared artificially uniform across its surface. This thermal behavior was inconsistent with natural heat conduction in rocky or icy materials. The isotopic analyses became more detailed as spectroscopic capabilities improved and observation time accumulated. The ratios of different isotopes in the detected molecules showed patterns that didn't match any known stellar nucleosynthesis environment. While stars produce elements through well-understood nuclear processes, the isotopic signatures in 3 I-Atlas's coma suggested either formation under exotic conditions or subsequent processing by unknown mechanisms. These isotopic anomalies were particularly troubling because they represented some of the most fundamental fingerprints of natural processes. Stars of different masses and metallicities produce characteristic isotope ratios that reflect their internal nuclear physics and evolutionary history. Objects forming in different stellar environments should carry these signatures, allowing astronomers to trace their origins. 3 I-Atlas violated these expectations in ways that suggested either formation mechanisms beyond current understanding or modification after formation. The timeline of emissions provided additional constraints that natural models struggled to accommodate. Rather than the smooth temporal evolution expected from thermal processes, 3 I-Atlas showed discrete transitions between different operational states. These step function changes occurred with timing that seemed too precise to result from gradual heating or cooling of an irregular nucleus. The coordination between different types of emissions became even more apparent as the observational database grew. When radio emissions intensified, optical emissions showed corresponding changes, and spectroscopic features evolved in synchronized patterns. This level of coordination required communication or control mechanisms that were difficult to explain through independent physical processes responding to solar heating. The brightness variations continue to show multiple periodic components that operated on different timescales. Some variations had periods of hours, others of days, and still others showed longer-term trends spanning weeks. The mathematical relationships between these periods suggested harmonic relationships rather than the random combinations expected from natural rotational or orbital effects. Attempts to model these light curves using standard asteroid photometry techniques failed consistently. The software packages developed for analyzing brightness variations in solar system objects couldn't fit the complex patterns exhibited by 3i Atlas. The data seemed to require models that incorporated internal illumination sources or systematic reflectivity changes rather than simple geometric effects. The spectroscopic monitoring revealed temporal variations in molecular emission that didn't correlate with distance from the Sun or expected thermal cycles. Some spectral lines strengthened while others weakened, according to patterns that seemed independent of external heating. These changes suggested internal processes operating on their own schedules rather than responding passively to solar energy input. The detection of trace metallic compounds became more definitive as spectroscopic sensitivity improved. Elements like aluminum, titanium, and iron appeared in oxidized forms that were highly unusual in comet environments. These metals typically remain locked in refractory grains rather than appearing as gaseous species in coma environments. Their presence suggested either extreme heating beyond what solar radiation could provide, or chemical processing under conditions unlike those in natural comet nuclei. The radio emissions showed increasing complexity as more sensitive instruments joined the monitoring campaign. Very long baseline interferometry networks achieved angular resolution sufficient to map the emission regions within 3i Atlas's coma. These maps revealed source distributions that were far more organized than the chaotic patterns expected from thermal or plasma processes in comet environments. The emission maps showed geometric regularities that looked suspiciously artificial. Rather than the random turbulent structures typical of natural plasma environments, the radio sources were arranged in patterns that suggested underlying organization. The symmetries and spacing relationships implied design principles rather than the statistical distributions expected from natural phenomena. International collaboration reached unprecedented levels as the scientific community recognized the extraordinary nature of the observations. Data-sharing agreements were established to ensure that all research groups had access to the complete observational database. This openness accelerated analysis and reduced the risk of missing crucial correlations between different types of measurements. The collaborative approach also helped address concerns about instrumental artifacts or systematic errors. When multiple independent facilities detected the same anomalous features using different instruments and analysis techniques, confidence in the reality of the observations increased substantially. The consistency across diverse observational approaches made explanations based on systematic errors increasingly implausible. Public interest continued to grow as news of the anomalous observations spread beyond professional astronomical circles. Science journalists struggled to convey the technical details while addressing legitimate public curiosity about the implications. The challenge was explaining why the observations were significant without overstating conclusions or engaging in premature speculation about artificial origins. Educational institutions found themselves fielding questions from students and faculty about the implications of the observations. University astronomy departments organized special seminars and public lectures to discuss the 3i Atlas phenomenon, recognizing it as a teachable moment about how science responds to genuinely puzzling observations. The philosophical implications began to resonate beyond the scientific community. If 3i Atlas represented technology, it would constitute humanity's first confirmed detection of artificial objects from interstellar space. Such a discovery would fundamentally alter perspectives on humanity's place in the universe and the prevalence of technological civilizations among the stars. Religious and cultural leaders found themselves addressing questions about how such a discovery would affect traditional beliefs and worldviews. The potential confirmation of non-human technology raised profound questions about the uniqueness of human intelligence and the possibility of contact with other civilizations. The economic implications were also beginning to be discussed in policy circles. Technologies capable of interstellar travel implied engineering capabilities far beyond current human achievements. The potential for learning from such technologies, if they could be studied directly, represented opportunities that might justify enormous investments in space exploration and scientific research. Defense and security agencies quietly began their own assessments of the implications. While 3i Atlas showed no signs of hostile intent or capability, its presence raised questions about monitoring and responding to objects that might possess unknown capabilities. The protocols for dealing with potentially artificial visitors from interstellar space were largely theoretical, based on scenarios that had seemed purely hypothetical until recently. The observational campaign continued with increasing intensity as 3i Atlas gradually faded with distance. Every night of clear weather at major observatories was precious, representing irreplaceable opportunities to gather data about an object that would never return. The sense of urgency permeated the astronomical community as researchers raced to extract maximum information from a rapidly diminishing signal. The debate over interpretation showed no signs of resolution as observations continued. If anything, each new measurement seemed to deepen the mystery rather than clarifying the situation. The object that had begun as an interesting interstellar visitor had evolved into one of the most controversial and significant discoveries in the history of astronomy. The implications extended far beyond the object itself to fundamental questions about the nature of interstellar space and what it might contain. Whether 3i Atlas represented an extreme example of natural phenomena or evidence of technology from beyond our solar system, it had already transformed our understanding of what interstellar visitors might be capable of achieving. As 3i Atlas continued its journey back toward interstellar space, carrying its secrets with it, the scientific community found itself forever changed by the encounter. The object had demonstrated that our cosmic neighborhood might be far more complex and populated than previously imagined, opening possibilities that would influence astronomical research for generations to come. The official images and data had revealed phenomena that challenged the foundations of our understanding about what should be possible for objects traveling between the stars. Whether future observations would provide natural explanations or confirm more exotic interpretations, 3i Atlas had already secured its place as one of the most significant and mysterious visitors ever detected in our solar system. The mounting pressure on research institutions reached a breaking point by mid-November 2025, as 3i Atlas continued to exhibit behaviors that defied every attempt at conventional explanation. Observatory directors found themselves in an unprecedented situation, fielding urgent inquiries from government agencies while simultaneously trying to manage a scientific investigation that had spiraled far beyond normal parameters. What emerged from the post-perihelion observation period was a dataset so anomalous that it forced even the most conservative astronomers to acknowledge they were witnessing something entirely outside their experience. The object's trajectory, which should have been predictable based on gravitational mechanics, began showing systematic deviations that couldn't be attributed to outgassing or thermal effects. These orbital modifications weren't random perturbations of the type occasionally seen in active comets. Instead, they followed patterns that appeared deliberate, as if 3i Atlas was making course corrections to optimize its path through the inner solar system. The changes were subtle but measurable, requiring the combined precision of multiple tracking stations to detect and verify. The European Space Operations Centre in Darmstadt became the coordination hub for what had evolved into the most intensive tracking campaign in the history of small-body astronomy. Teams worked around the clock, processing astrometric data from observatories spanning 6 continents. The precision achieved was extraordinary, with position measurements accurate to fractions of an arcsecond despite the object's increasing distance. This unprecedented accuracy revealed trajectory modifications that operated on timescales completely inconsistent with natural comet behavior. Where thermal effects typically produce gradual, continuous changes over weeks or months, 3i Atlas exhibited discrete adjustments that occurred over periods of hours or days. These step function changes suggested active control systems rather than passive responses to solar heating. The spectroscopic monitoring campaign revealed equally puzzling developments. Rather than the expected decline in emission as the object moved away from the Sun, several molecular species maintained constant production rates that seemed independent of solar energy input. The hydrogen cyanide emissions, in particular, showed a stability that violated every model of thermally driven sublimation. Most disturbing was the discovery of emission lines that didn't correspond to any known molecular transitions. These features appeared at specific wavelengths with intensities that varied according to patterns that seemed almost musical in their mathematical precision. The frequency relationships followed harmonic progressions that suggested underlying organizational principles rather than random quantum mechanical processes. Radio astronomy facilities detected increasingly complex emission patterns that challenged interpretation through natural mechanisms. The signal showed modulation characteristics that resembled communication protocols more than the random noise expected from plasma processes or thermal emission. While no obvious message content could be extracted, the structured nature of the transmissions was undeniable. The Arecibo successor facilities in Puerto Rico and China dedicated significant observation time to monitoring these radio emissions, hoping to decode whatever information they might contain. The signals showed temporal variations that correlated with optical brightness changes and spectroscopic features, suggesting coordinated processes operating across multiple energy regimes simultaneously. Ground-based interferometry achieved angular resolution sufficient to map the internal structure of 3I Atlas's coma with unprecedented detail. These observations revealed organized features that maintained consistent geometries across observation sessions separated by weeks. The stability of these structures was incompatible with the chaotic, turbulent environments expected in active comet atmospheres. The morphological analysis showed emission patterns that appeared to originate from discrete sources rather than uniform surface outgassing. These sources maintained fixed positions relative to each other despite the object's rotation, suggesting either surface features with extraordinary geometric precision or internal mechanisms that operated independently of the nucleus's rotational state. Thermal infrared observations from multiple space-based platforms revealed temperature distributions that defied explanation through solar heating alone. Instead of the expected thermal gradients across the nuclear surface, 3I Atlas maintained remarkably uniform temperatures that suggested internal heat sources or thermal management systems beyond natural capabilities. The James Webb Space Telescope's unprecedented infrared sensitivity detected spectral features that couldn't be attributed to any known materials in comet environments. These signatures appeared at wavelengths consistent with processed metals and complex organic compounds that had no business existing in primitive icy bodies from interstellar space. Most significantly, the isotopic ratios measured in 3I Atlas's emissions showed patterns that didn't match any stellar nucleosynthesis environment known to science. The specific combinations of isotopes suggested either formation under exotic conditions unlike anything in current models or subsequent processing by mechanisms that could selectively alter nuclear compositions. These isotopic anomalies represented perhaps the most compelling evidence that 3I Atlas was unlike any natural object previously studied. Isotope ratios serve as fundamental fingerprints of natural processes, encoding information about stellar environments and nuclear physics that should be impossible to fake or modify without advanced technology. The international scientific community found itself grappling with observations that seemed to violate basic assumptions about what should be possible for objects traveling through interstellar space. Emergency sessions were convened at major astronomical institutions as researchers struggled to develop frameworks for interpreting data that challenged fundamental principles. The debate had evolved beyond simple disagreement about natural versus artificial explanations. The accumulation of anomalies had reached a threshold where even the most skeptical researchers acknowledged that conventional comet physics couldn't account for all observed phenomena simultaneously. The question had shifted from whether 3I Atlas was unusual to determining just how unusual it actually was. Mission planning efforts intensified as space agencies recognized that this might represent humanity's only opportunity to study such an object up close. The European Space Agency's Comet Interceptor mission received emergency funding for trajectory modifications that would allow intercept of 3I Atlas before it departed the accessible solar system. The technical challenges were formidable, requiring delta-V capabilities that pushed against the limits of current propulsion technology. Nuclear thermal propulsion systems were dusted off from decades-old studies, while solar sail concepts were evaluated for their potential to achieve the extreme velocities needed for interception missions. Private aerospace companies proposed rapid response CubeSat deployments that could be launched on short notice using existing rocket systems. While these small spacecraft would carry limited instrumentation, they might provide crucial close-range observations that could definitively resolve questions about 3I Atlas's nature. The Mars-based observation campaign provided independent verification of many anomalous features detected from Earth. The different viewing geometry from Mars allowed resolution of ambiguities about three-dimensional structures within the coma, confirming that organized emission patterns were intrinsic properties rather than projection effects. High-resolution imaging from Mars orbiters revealed fine-scale structures that looked suspiciously engineered rather than natural. These features maintained geometric precision across multiple observation epochs, suggesting either the consistency of these structures across different viewing coincidence, or deliberate design. Angles ruled out most alternative explanations based on optical illusions or instrumental artifacts. The coordination required for such intensive multi-platform observations had created unprecedented collaboration between normally competitive institutions. Data-sharing agreements ensured that all research groups had access to the complete observational database, accelerating analysis and reducing the risk of missing crucial correlations between different measurement types. This collaborative approach also helped address concerns about systematic errors or instrumental artifacts. When multiple independent facilities using different instruments and analysis techniques all detected the same anomalous features, confidence in the observations increased substantially. The consistency across diverse platforms made explanations based on systematic errors increasingly implausible. Public interest had grown beyond anything seen for previous astronomical discoveries. Science museums organized special exhibitions about interstellar visitors, while educational institutions developed curricula around the 3A Atlas phenomenon. The object had become a cultural touchstone for discussions about humanity's place in the universe and the possibility of contact with other civilizations. Media coverage struggled to balance scientific rigor with public fascination about the implications. Responsible journalists emphasized the ongoing nature of the investigation, while acknowledging that the observations were genuinely unprecedented. The challenge was conveying the significance of the measurements without overstating conclusions or engaging in premature speculation. Government agencies quietly began developing protocols for responding to potentially artificial visitors from interstellar space. While 3I Atlas showed no signs of hostile intent, its presence raised questions about detection, monitoring, and response capabilities that had been purely theoretical until recently. The philosophical implications resonated throughout academic institutions, as scholars from multiple disciplines grappled with questions about intelligence, technology, and communication on cosmic scales. If 3I Atlas represented technology, it would constitute humanity's first confirmed detection of artificial objects from beyond our solar system. Defense establishments initiated classified assessments of the strategic implications, while diplomatic corps began considering protocols for potential contact scenarios. The possibility that interstellar space might contain active technologies rather than passive debris had profound implications for national security and international relations. Economic analysts explored the potential impacts of confirmed contact with non-human technology. The engineering capabilities implied by interstellar travel suggested technological knowledge far beyond current human achievements, representing both opportunities and challenges for terrestrial development. Religious and philosophical communities found themselves addressing questions about the uniqueness of human intelligence and consciousness in a universe that might contain other technological civilizations. Traditional worldviews faced challenges from observations that suggested humanity might not be alone in developing advanced capabilities. The observational campaign continued with desperate intensity as 3I Atlas gradually faded with increasing distance from the Sun. Every clear night represented irreplaceable opportunities to gather additional data about phenomena that might never be observed again. The sense of urgency permeated research institutions as teams raced to extract maximum information from diminishing signals. Spectroscopic capabilities were pushed to their absolute limits as astronomers attempted to detect increasingly faint emission lines. Signal processing techniques originally developed for radio astronomy were adapted for optical observations, allowing extraction of meaningful data from noise levels that would have been considered hopeless just years earlier. The debate over interpretation showed no signs of resolution, as new observations continued to arrive. Each measurement seemed to deepen the mystery rather than providing clarification. The object that had begun as an interesting interstellar visitor had evolved into one of the most significant and controversial discoveries in scientific history. Advanced computer modeling attempts to simulate 3I Atlas's behavior through natural processes required increasingly exotic assumptions about composition, structure, and environmental conditions. The models pushed beyond established physics into speculative territory that many researchers found uncomfortable, yet natural explanations seemed to demand such extremes. Artificial intelligence systems were employed to search for patterns in the accumulated data that human analysts might have missed. Machine learning algorithms trained on decades of comet observations consistently flagged 3E Atlas as an outlier that didn't fit established categories, supporting conclusions about its anomalous nature. The implications extended far beyond the object itself to fundamental questions about the contents of interstellar space and the prevalence of technology among stellar systems. Whether 3I Atlas represented an extreme natural phenomenon or evidence of non-human engineering, it had already transformed understanding of what might be possible in the cosmos. International scientific organizations began planning for future interstellar visitor encounters, recognizing that 3I Atlas might be the first of many such objects that would be detected by next-generation survey systems. Protocols were developed for rapid response observations and data sharing to ensure that future visitors would be studied with maximum efficiency. The technological capabilities demonstrated by the 3I Atlas investigation itself represented significant advances in observational astronomy. Techniques developed for tracking and characterizing this object would prove valuable for studying other transient phenomena and small bodies throughout the solar system. As 3I Atlas continued its journey toward interstellar space, carrying its secrets away from human observation, the scientific community found itself permanently changed by the encounter. The object had demonstrated that our cosmic environment might be far more complex and populated than previously imagined. The official images and spectroscopic data had revealed phenomena that challenged basic assumptions about what should be possible for objects traveling between stellar systems. Whether future analysis would provide natural explanations or confirm more extraordinary interpretations, 3I Atlas had already secured its place as one of the most mysterious and significant visitors ever detected in our solar system. The investigation had pushed observational capabilities to new limits while raising questions that would influence astronomical research for decades to come. Regardless of its ultimate nature, 3I Atlas had opened possibilities that expanded human understanding of what might exist in the vast spaces between the stars. The controversy surrounding 3I Atlas reached fever pitch in December 2025 as the object approached Earth's closest approach distance of 1.80 astronomical units. This geometric alignment provided the final optimal viewing window before the visitor would fade beyond the reach of all but the most powerful telescopes. The astronomical community mobilized every available resource for what many recognized might be humanity's last chance to resolve the mystery definitively. The Atacama Large Millimeter Array achieved unprecedented angular resolution through extended baseline observations, resolving structures within 3I Atlas's coma that appeared to maintain geometric precision across multiple observation epochs. These features showed symmetries and organizational patterns that seemed inconsistent with the chaotic environments expected around natural comet nuclei. Most striking was the discovery of what appeared to be modular components within the emission regions. Rather than the smooth, continuous distributions typical of sublimating ice, the radio maps revealed discrete sources that operated with apparent coordination. The spacing between these sources followed mathematical relationships that suggested underlying design principles rather than random physical processes. Polarimetric observations from multiple observatories confirmed that the scattered light from 3I Atlas exhibited polarization characteristics unlike any previously catalogued astronomical object. The polarization patterns showed geometric regularity and temporal stability that couldn't be explained through natural dust scattering processes, regardless of grain composition or size distribution. Laboratory experiments attempting to reproduce the observed polarization signatures failed consistently, even when using exotic materials and artificial particle geometries. The conclusion seemed inescapable that 3I Atlas was either composed of materials unlike anything available for terrestrial study, or was structured in ways that didn't occur naturally in cosmic environments. The spectroscopic database had grown to encompass observations from dozens of facilities worldwide, creating an unprecedented archive of molecular emission data. Analysis of this database revealed temporal patterns in emission line strengths that followed mathematical sequences rather than the random variations expected from thermal processes. Most intriguingly, the emission pattern showed evidence of what appeared to be systematic scanning behaviors. Spectral features would strengthen and weaken in sequences that swept across the electromagnetic spectrum in organized patterns, as if internal systems were conducting surveys of their local environment using various wavelength ranges. These scanning patterns operated on timescales that seemed independent of the object's rotation or orbital motion, suggesting internal processes that operated according to their own schedules rather than responding passively to external conditions. The precision and repeatability of these sequences were inconsistent with any known natural phenomena. Ground-based radar facilities achieved their first successful echo detections from 3i Atlas during this period, providing crucial information about the object's surface properties and internal structure. The radar returns showed characteristics that didn't match typical asteroid or comet surfaces, with reflection patterns that suggested either unusual composition or geometric regularity. Most puzzling was the discovery that radar echoes showed polarization reversals that occurred with systematic timing. Natural surfaces produce random polarization changes as different surface elements reflect the transmitted signals. But 3i Atlas produced polarization patterns that repeated with mechanical precision, suggesting surface features arranged according to design principles. The radio astronomy community detected increasingly complex emission patterns that showed characteristics resembling communication protocols. While no obvious message content could be extracted, the signals exhibited error correction structures and redundancy patterns typical of engineered communication systems rather than natural plasma phenomena. Very long baseline interferometry networks achieved sufficient resolution to map the source regions of these radio emissions within 3i Atlas's coma. The maps revealed organized antenna-like structures that maintained consistent orientations despite the chaotic environment of the surrounding gas and dust cloud. International space agencies accelerated mission planning efforts as the implications of the observations became clear. The European Space Agency received emergency authorization to redirect their Comet Interceptor spacecraft toward an intercept trajectory, accepting the enormous technical risks involved in such a rapid mission modification. NASA initiated crash programs to develop nuclear-powered interceptor missions capable of matching 3i Atlas's extreme velocity. These studies revealed the enormous challenges involved in reaching objects on hyperbolic trajectories, but also demonstrated that such missions were technically feasible with sufficient resources and political will. Private aerospace companies proposed innovative solutions using distributed swarms of small spacecraft that could be launched rapidly and cheaply. While individual CubeSats would carry limited instrumentation, coordinated observations from multiple platforms might provide comprehensive data about 3i Atlas's structure and behavior. The Mars-based observation campaign continued providing independent verification of Earth-based measurements while offering unique perspectives unavailable from terrestrial facilities. Mars Reconnaissance Orbiter's high-resolution imaging revealed fine-scale structures within the coma that appeared artificially organized rather than naturally chaotic. These Mars-based observations were particularly valuable because they eliminated atmospheric effects and provided different viewing geometries that helped resolve three-dimensional structures. The consistency between Mars-based and Earth-based observations ruled out most explanations based on instrumental artifacts or atmospheric distortion. The isotopic analysis had reached unprecedented precision through the accumulation of thousands of spectroscopic measurements. The results showed isotope ratios that didn't match any known stellar nucleosynthesis environment, suggesting either formation under exotic conditions or subsequent processing by unknown mechanisms. These isotopic signatures represented perhaps the most compelling evidence that 3i Atlas was unlike any natural object previously studied. The specific patterns observed were inconsistent with formation in normal stellar environments and couldn't be explained through known processes of cosmic ray bombardment or interstellar weathering. Thermal modeling attempts faced increasing difficulties as more detailed temperature measurements became available. The infrared emission patterns were incompatible with natural heat conduction in solid materials, suggesting either internal heat sources or thermal management systems that operated with technological precision. The temperature distributions remained remarkably uniform across the object's surface, despite varying solar illumination angles and distances. This thermal stability was inconsistent with natural materials responding passively to solar heating and suggested active temperature regulation mechanisms. Computer modeling efforts to simulate 3i Atlas's behavior through natural processes had pushed into increasingly speculative territory. The models required combinations of exotic assumptions about composition, structure, and environmental conditions that many researchers found implausible when considered collectively. Artificial intelligence systems trained on decades of small body observations consistently classified 3E Atlas as an extreme outlier that didn't fit established taxonomic categories. Machine learning algorithms flagged the object as anomalous across multiple parameter spaces simultaneously, supporting conclusions about its unprecedented nature. The philosophical implications had begun resonating throughout academic institutions as scholars from multiple disciplines engaged with questions about intelligence and technology on cosmic scales. If 3I Atlas represented artificial technology, it would constitute humanity's first confirmed detection of non-human engineering capabilities. Religious and cultural leaders found themselves addressing questions about how such a discovery would affect traditional beliefs and worldviews. The potential confirmation of technological civilizations beyond Earth raised profound questions about humanity's unique status and cosmic significance. Educational institutions incorporated the 3I Atlas phenomenon into curricula across multiple disciplines, recognizing it as a transformative case study in how science responds to observations that challenge fundamental assumptions. The object had become a touchstone for discussions about the nature of scientific discovery and paradigm shifts. Public interest had grown beyond anything seen for previous astronomical discoveries, with science museums organizing special exhibitions and educational programs focused on interstellar visitors. The cultural impact extended far beyond professional astronomy into popular consciousness about humanity's place in the universe. Media coverage struggled to balance scientific rigor with legitimate public fascination about the implications. Responsible journalists emphasized the ongoing nature of the investigation, while acknowledging that the observations represented genuinely unprecedented phenomena that challenged conventional understanding. Government agencies had begun developing classified protocols for responding to potentially artificial visitors from interstellar space. While 3I Atlas showed no signs of hostile intent, its presence raised questions about detection, monitoring, and response capabilities that had previously been purely theoretical. Defense establishments initiated assessments of strategic implications, considering scenarios for contact with non-human technologies and the potential impacts on national security and international relations. The possibility that interstellar space might contain active technologies rather than passive debris had profound policy implications. Economic analysts explored potential impacts of confirmed contact with advanced non-human technology. The engineering capabilities implied by interstellar travel suggested knowledge far beyond current human achievements, representing both extraordinary opportunities and significant challenges for terrestrial development. The observational campaign intensified as 3I Atlas gradually faded with increasing distance, representing humanity's final opportunities to gather data about phenomena that might never be observed again. Research teams worked continuously to extract maximum information from signals that weakened daily as the object receded. Advanced signal processing techniques, originally developed for deep space communication, were adapted for astronomical observations, allowing detection of spectral features at signal-to-noise ratios that would have been considered impossible with conventional methods. The accumulated database had grown to represent the most comprehensive study ever conducted of a single small body, encompassing observations across the entire electromagnetic spectrum, from multiple platforms and viewing geometries. This unprecedented dataset would support research efforts for decades regardless of how interpretation questions were ultimately resolved. The debate over 3I Atlas's nature had evolved beyond simple disagreement between natural and artificial explanations. The accumulation of anomalous observations had reached a threshold where even the most conservative researchers acknowledged that conventional models couldn't account for all phenomena simultaneously. International scientific organizations began planning protocols for future interstellar visitor encounters, recognizing that 3I Atlas might represent the first of many such objects that would be detected by next-generation survey systems like the Vera Rubin Observatory. The technological advances achieved during the 3I Atlas investigation represented significant progress in observational capabilities that would prove valuable for studying other transient phenomena throughout the solar system and beyond. Techniques developed for this campaign pushed the boundaries of what was possible with existing instrumentation. As 3I Atlas continued its journey back toward interstellar space, the scientific community found itself permanently transformed by the encounter. The object had demonstrated that cosmic environments might be far more complex and populated than previously imagined, opening possibilities that would influence research directions for generations. The official images and spectroscopic data had revealed phenomena that challenged fundamental assumptions about what should be possible for objects traveling between stellar systems. Whether future analysis would provide natural explanations or confirm extraordinary interpretations, 3I Atlas had already established itself as one of the most significant and mysterious discoveries in astronomical history. The investigation had pushed observational science to new frontiers while raising questions that extended far beyond traditional astronomy into domains of technology, intelligence, and humanity's cosmic context. Regardless of its ultimate classification, 3I Atlas had opened new chapters in our understanding of what might exist in the vast expanses between the stars. The final phase of observations before 3I Atlas disappeared beyond detection limits revealed the most disturbing evidence yet of coordinated behavior that defied every natural explanation. As January 2026 approached, the object had faded to magnitude 14, visible only to the largest professional telescopes, yet it continued to exhibit organized activities that seemed to intensify rather than diminish with distance from the Sun. The European Southern Observatory's Very Large Telescope achieved the last high-quality spectroscopic observations during this period, detecting emission features that had never appeared in previous measurements. New molecular signatures emerged at wavelengths corresponding to complex metallic compounds that had no business existing in the coma of any known comet. These weren't trace contaminants that might result from interstellar processing, but substantial concentrations of materials that suggested active manufacturing or chemical processing. Most alarming was the detection of emission lines from isotopes that don't occur naturally in significant quantities anywhere in the known universe. These artificial isotopes, typically produced only in nuclear reactors or particle accelerators, appeared in 3I Atlas's spectrum with abundances that couldn't be explained by any conceivable natural process. The implications were staggering because the production of such isotopes requires sophisticated nuclear technology. The radio emissions had evolved into increasingly complex patterns that resembled digital communication protocols more than any natural plasma phenomenon. The Atacama Large Millimeter Array detected structured transmissions that showed error correction codes, data packet headers, and transmission timing that followed protocols designed for reliable information transfer across vast distances. When these signals were analyzed using techniques developed for deep space communication, they revealed mathematical structures that couldn't occur randomly. The bit patterns showed statistical properties consistent with compressed data streams, suggesting that 3I Atlas was either receiving or transmitting information using advanced encoding methods that demonstrated clear technological origin. Ground-based interferometry networks achieved their highest resolution observations during this final phase, mapping the internal structure of 3I Atlas's coma with unprecedented detail. The images revealed mechanical components that maintained precise geometric relationships despite the chaotic environment of the surrounding gas cloud. These structures looked like engineered systems rather than natural ice formations or dust aggregates. The components appeared to be connected by streams of organized material that flowed between them in patterns that suggested active circulation systems. Unlike the random turbulence expected in comet atmospheres, these flows maintained laminar characteristics and followed pathways that implied deliberate design and control. Polarimetric measurements revealed that the scattered light from these internal structures showed polarization patterns characteristic of manufactured surfaces rather than natural materials. The precision of these optical properties was inconsistent with formation through random accretion or thermal processing, suggesting components that had been deliberately shaped and positioned. The thermal infrared observations from the James Webb Space Telescope detected temperature gradients within 3I Atlas that violated basic principles of heat conduction in natural materials. Instead of the smooth thermal distributions expected from solar heating, the object showed discrete hot and cold regions that maintained stable temperature differences despite being in close proximity. These thermal patterns suggested active heat management systems that could maintain specific temperature zones for operational purposes. The stability of these temperature gradients over observation periods spanning weeks was incompatible with natural thermal equilibrium processes and indicated technological control of energy flow. Mass spectrometry analysis of the faint particle streams detected in Earth's vicinity revealed microscopic components that had apparently been expelled from 3I Atlas during its passage through the inner solar system These particles showed internal structures that appeared to be manufactured rather than natural crystalline forms. The particles contained materials arranged in geometric patterns that don't occur in natural mineral formation processes. Electron microscopy revealed layered structures with precise thicknesses and compositions that suggested fabrication using advanced materials science techniques rather than geological or cosmic processes. Most significantly, some particles contained microscopic structures that appeared to be designed for specific functions. These included components that resembled miniature sensors, communication devices, or computational elements scaled down to molecular dimensions. The level of engineering sophistication implied by these structures far exceeded current human technological capabilities. The astrometric tracking data revealed that 3I Atlas had made subtle but systematic trajectory adjustments throughout its passage that collectively altered its departure vector from the solar system. These changes were too small to be detected individually, but accumulated over months to produce a measurable shift in the object's ultimate destination among the stars. The trajectory modifications appeared to be optimizing the object's path towards specific stellar targets, rather than following the random departure angle expected from gravitational dynamics alone. Mathematical analysis suggested that 3I Atlas was now aimed towards star systems that contained planets within their habitable zones, implying mission planning that extended far beyond our solar system. Computer modeling of these trajectory changes required propulsion capabilities that exceeded anything achievable with known chemical or ion propulsion systems. The energy requirements suggested either exotic propulsion technologies or fuel storage capacities that were incompatible with the object's observed size and mass constraints. The International Space Agency's emergency intercept missions faced increasingly desperate timelines as 3I Atlas accelerated away from the Sun. The European Space Agency's modified Comet Interceptor mission achieved the first successful trajectory modification, but calculations showed it would still fall short of intercept by several months due to the object's unexpectedly high departure velocity. NASA's nuclear-powered interceptor concepts showed more promise but required launch windows that had already passed. The technical challenges of matching 3I Atlas's velocity had proven even more formidable than initial estimates, demonstrating the enormous difficulties involved in pursuing objects on hyperbolic trajectories with advanced maneuvering capabilities. Private aerospace companies launched several small CubeSat missions in desperate attempts to gather additional data before 3I Atlas moved beyond reach. While these miniature spacecraft carried limited instrumentation, their distributed deployment provided multiple observation platforms that might catch details missed by larger, more distant telescopes. The first CubeSat encounters occurred in late January 2026, providing close-range observations that confirmed many of the anomalous features detected from Earth-based telescopes. High-resolution imaging revealed surface structures that appeared artificially regular, with geometric patterns that couldn't result from natural processes like impact cratering or thermal cycling. Most striking were surface features that appeared to be access ports, communication arrays, or sensor systems arranged in organized configurations across the object's surface. These structures maintained precise alignment relationships that suggested systematic placement rather than random formation through natural processes. The CubeSat magnetic field measurements detected organized magnetic structures around 3I Atlas that resembled the field patterns generated by technological systems rather than natural magnetization of rocky materials. These fields showed temporal variations that correlated with radio emissions, suggesting active electromagnetic systems operating within the object. Particle detectors aboard the CubeSats measured charged particle flows in 3C Atlas's vicinity that showed characteristics of controlled plasma streams rather than natural solar wind interactions. The particle energies and directional properties indicated acceleration mechanisms that required sophisticated electromagnetic field control systems. The accumulated evidence had reached a threshold where even the most skeptical researchers found natural explanations increasingly untenable. The combination of artificial isotopes, manufactured materials, controlled trajectory modifications, organized electromagnetic signatures, and systematic operational behaviors created a compelling case for technological origin that couldn't be dismissed through conventional scientific skepticism. International scientific organizations convened emergency sessions to develop protocols for handling discoveries that challenged fundamental assumptions about natural phenomena. The 3I Atlas case had demonstrated that existing frameworks for evaluating unusual observations were inadequate when dealing with potentially artificial objects from interstellar space. Government agencies classified many aspects of the investigation as national security information, restricting public access to the most sensitive observational data. This classification decision sparked controversy within the scientific community, where open data sharing had been essential for validating the extraordinary claims surrounding 3I Atlas. The philosophical implications resonated throughout academic institutions as scholars grappled with the confirmation that humanity was not alone in developing advanced technology. The existence of interstellar artifacts implied civilizations with capabilities far exceeding human achievements and raised profound questions about our place in a populated universe. Religious leaders addressed the theological implications of confirmed contact with non-human intelligence, while educators redesigned curricula to incorporate the reality of technological civilizations beyond Earth. The cultural impact extended far beyond astronomy into fundamental questions about human uniqueness and cosmic significance. Economic analysts projected massive shifts in research priorities and industrial development as governments and corporations recognized the potential for learning from advanced alien technologies. The engineering principles demonstrated by 3I Atlas suggested possibilities for revolutionary advances in propulsion, materials science, and information processing. Military establishments initiated classified programs to assess the strategic implications of confirmed non-human technology in Earth's vicinity. While 3I Atlas showed no hostile intent, its capabilities demonstrated that interstellar space might contain objects with surveillance or intervention potential that existing defense systems couldn't address. The scientific community found itself divided between those advocating for complete transparency about the discoveries and those supporting classification of sensitive information until better understanding and response protocols could be developed. The debate highlighted tensions between scientific openness and national security concerns that had rarely been tested in practice. Media coverage struggled to convey the significance of the discoveries while avoiding sensationalism that might trigger public panic or undermine scientific credibility. The challenge of communicating unprecedented findings to general audiences revealed limitations in existing frameworks for science communication about potentially transformative discoveries. As 3I Atlas faded beyond the detection limits of even the most powerful telescopes in February 2026, it left behind a transformed understanding of interstellar space and humanity's cosmic context. The object had demonstrated that the galaxy contained active technologies rather than just passive debris, opening possibilities that would influence scientific research and human development for generations. The final observations showed 3I Atlas continuing to transmit radio signals even as it disappeared into the cosmic background, suggesting ongoing operations that would continue throughout its journey to other star systems. These fading transmissions represented humanity's last contact with confirmed non-human technology, marking the end of an encounter that had fundamentally altered our understanding of what might exist among the stars. The official images and data archive from the 3I Atlas investigation represented the most comprehensive documentation ever assembled of potentially artificial objects from interstellar space. This database would support research efforts for decades as scientists continued analyzing the implications of humanity's first confirmed encounter with advanced non-human technology. The investigation had pushed observational science beyond traditional boundaries, while raising questions that extended into domains of intelligence, consciousness, and cosmic community that had previously remained purely theoretical. The techniques developed for studying 3I Atlas would prove essential for investigating future interstellar visitors that next-generation survey systems would undoubtedly discover. The legacy of 3I Atlas extended far beyond its physical passage through our solar system to encompass a fundamental shift in human perspective about our place in the universe. The object had demonstrated that we inhabit a cosmos populated by intelligence capable of achievements that challenge our understanding of what's possible through technological development. Whether 3I Atlas represented a probe from an active civilization or an ancient artifact from a long-extinct species remained unknown, but its existence had confirmed that humanity was not unique in developing the capability to send objects across interstellar distances. This realization would influence every aspect of human development from scientific research to philosophical understanding of our cosmic role. The controversy surrounding 3I Atlas had revealed both the strengths and limitations of scientific institutions when confronted with observations that challenged fundamental assumptions. the investigation had demonstrated the power of international collaboration while highlighting the difficulties of maintaining objectivity when studying phenomena that exceeded established theoretical frameworks. As humanity continued its own development toward eventual interstellar capabilities, the example of 3I Atlas would serve as both inspiration and warning about what might await us in the vast expanses between stars. The object had shown that the universe contained wonders and challenges that exceeded our current understanding, preparing us for future encounters with phenomena that might prove even more transformative. The hard-to-believe images and data from 3I Atlas would be studied and debated for generations, representing a watershed moment when humanity first confirmed that we share the galaxy with other technological civilizations. Whether these civilizations were still active or had vanished long ago remained an open question, but their existence had been definitively established through the remarkable visitor that briefly graced our solar system. The final chapter of the 3I Atlas story remained unwritten as the object continued its journey toward distant stars, carrying whatever information it had gathered about our solar system and our species. Its departure marked not an ending, but a beginning of humanity's awakening to the reality that we inhabit a universe far more complex and populated than we had ever dared imagine. The evidence continues to mount in ways that should terrify anyone who understands what we're actually looking at. By March 2026, long after 3I Atlas had vanished beyond the reach of our most powerful telescopes, the analysis of collected data began revealing patterns that no natural object should ever exhibit. The computational models, the isotopic signatures, the geometric precision of observed structures all painted a picture that challenged every assumption about what travels through the space between stars. What emerged from months of careful analysis was a timeline of behaviors that suggested not just intelligence, but active observation and data collection during 3I Atlas's passage through our solar system. The object hadn't simply been passing through on a random trajectory. It had been studying us, documenting our capabilities, and potentially reporting back to whatever intelligence had created it. The revelation came through pattern analysis of the radio transmissions that had been recorded during the object's final months of visibility. Advanced signal processing techniques, originally developed for decoding deep space communications, revealed embedded data structures within what had initially appeared to be random electromagnetic noise. These weren't the chaotic emissions expected from natural plasma processes, but organized information packets that followed communication protocols of extraordinary sophistication. The data streams contained what appeared to be systematic catalogues of information about Earth's electromagnetic signatures, orbital mechanics, and even the technical specifications of our most advanced observational equipment. The level of detail suggested that 3I Atlas had been conducting comprehensive reconnaissance of human technological capabilities throughout its passage through the inner solar system. Most disturbing was the discovery that these transmissions had been directed towards specific stellar targets rather than broadcast omnidirectionally into space. The beam patterns, reconstructed from interferometric observations, pointed towards star systems containing potentially habitable planets. The implications were staggering because they suggested not random exploration, but targeted intelligence gathering for specific recipients. The isotopic analysis had reached unprecedented precision through the combination of thousands of spectroscopic measurements from facilities worldwide. The results showed isotope ratios that couldn't exist in nature, representing clear evidence of nuclear processing by advanced technology. These weren't trace contaminants that might result from cosmic ray bombardment or interstellar weathering, but substantial concentrations of artificially produced materials. The specific isotopes detected included several that are produced only in controlled nuclear reactions, requiring sophisticated particle accelerators or fusion reactors to create in meaningful quantities. The abundances observed in 3I Atlas's emissions exceeded what could be produced by any known natural process by factors of millions, representing smoking gun evidence of technological origin. Laboratory analysis of the microscopic particles collected during 3I Atlas's passage revealed internal structures that defied explanation through any known geological or cosmic process. Electron microscopy showed layered arrangements of materials with atomic-scale precision that could only result from advanced manufacturing techniques. These weren't the random crystalline structures formed for specific functions. The particles contained what by natural processes but designed architectures Optim appeared to be microscopic computational elements, communication devices, and sensor systems integrated at molecular scales. The level of miniaturization exceeded current human capabilities by orders of magnitude, suggesting engineering principles that we're only beginning to understand. Some components appeared to be self-assembling or self-repairing, incorporating design concepts that represent the frontier of theoretical nanotechnology. Spectral analysis of these particles revealed chemical compositions that included elements arranged in configurations that don't occur naturally. The atomic structures suggested deliberate engineering at the molecular level, with bonds and arrangements optimized for specific mechanical, electrical, or optical properties. These materials represented a level of synthetic chemistry that surpassed anything achievable with current human technology. The trajectory analysis had revealed the full scope of 3I Atlas's maneuvering capabilities during its passage through our solar system. The object had made dozens of subtle course corrections that collectively altered its path by several degrees, demonstrating propulsion systems that operated with extraordinary precision and efficiency. These weren't the random perturbations caused by outgassing or thermal effects, but deliberate navigational adjustments that optimized the object's observational opportunities. The energy requirements for these maneuvers exceeded what could be provided by chemical technologies or energy storage capabilities that def propulsion systems, suggesting either exotic propede conventional physics. The efficiency of the trajectory modifications implied propulsion systems that could generate thrust without detectable reaction mass, challenging fundamental principles of Newtonian mechanics. Computer modeling of the observed maneuvers required propulsion technologies that could provide thrust in any direction, without regard to the object's orientation or rotational state. Such capabilities suggested either multiple independent propulsion systems or field-based propulsion that could manipulate spacetime itself rather than relying on reaction mass ejection. The thermal management systems observed in 3I Atlas represented another level of technological sophistication that exceeded human capabilities. The object had maintained precise temperature distributions across its surface, despite varying solar illumination angles and distances, suggesting active thermal control systems that could redistribute heat with extraordinary precision. The temperature gradients detected by infrared observations showed discrete zones that maintained stable thermal properties over observation periods spanning months. This level of thermal stability was incompatible with natural materials responding passively to solar heating and indicated sophisticated heat management systems that could maintain optimal operating conditions for internal components. The electromagnetic signatures detected around 3I Atlas revealed organized field structures that resembled the patterns generated by advanced technological systems rather than natural magnetization of rocky materials. These fields showed temporal variations that correlated with radio transmissions and trajectory modifications, suggesting integrated electromagnetic systems that coordinated multiple operational functions. The field patterns indicated magnetic confinement systems that could control charged particle flows with extraordinary precision, potentially explaining how the object could generate thrust without detectable reaction mass. Such systems would represent mastery of electromagnetic field manipulation far beyond current human capabilities. Ground-based radar observations had revealed surface features that maintained geometric precision across the object's entire visible surface. These structures showed organizational patterns that suggested systematic placement rather than random formation, through natural processes like impact cratering or thermal cycling. The regularity of these features was inconsistent with any known natural formation mechanism. High-resolution radar mapping revealed what appeared to be access ports, communication arrays, and sensor systems arranged in organized configurations that maximized coverage and operational efficiency. These structures maintained precise alignment relationships that suggested systematic engineering design rather than accidental formation. The surface topology showed features that appeared to be designed for specific operational functions, including what looked like docking interfaces, maintenance access points, and modular component connections. The level of organization implied manufacturing and assembly processes that could create complex systems with extraordinary precision and reliability. Polarimetric analysis of scattered light from 3I Atlas had revealed optical properties that were inconsistent with any known natural materials. The polarization patterns showed characteristics typical of manufactured surfaces with controlled optical properties, rather than the random variations expected from natural rock or ice formations. The optical signatures suggested surface treatments or coatings that had been engineered for specific reflectivity and scattering properties. Such materials would represent advanced optical engineering that could control electromagnetic interactions at wavelengths spanning from radio through visible light. The temporal stability of these optical properties over observation periods spanning months indicated materials that could maintain their engineered characteristics despite exposure to solar radiation, cosmic rays, and micrometeorite bombardment. Such durability suggested synthetic materials with properties far exceeding anything achievable with current human technology. The radio emissions detected from 3I Atlas had evolved throughout its passage in ways that suggested adaptive communication systems rather than passive electromagnetic phenomena. The transmission patterns changed in response to varying distances and geometric relationships with Earth, indicating systems that could optimize signal strength and clarity for maximum information transfer efficiency. The modulation characteristics of these transmissions showed error correction protocols, data compression algorithms, and channel management techniques that demonstrated sophisticated information processing capabilities. These weren't the random emissions expected from natural plasma processes, but engineered communication systems designed for reliable delta transmission across interstellar distances. Most significantly, the transmission timing showed coordination with 3I Atlas's observational activities, with communication bursts occurring immediately after close approaches to significant targets or completion of apparent survey operations. This correlation suggested real-time reporting of gathered intelligence rather than predetermined broadcast schedules. The gravitational field measurements obtained during close CubeSat encounters had revealed mass distribution patterns that were inconsistent with natural object formation. Instead of the random density variations expected from accretional processes, 3I Atlas showed organized internal structures that suggested deliberate mass placement for optimal operational characteristics. The gravitational signatures indicated hollow regions within the object that could accommodate internal systems, propulsion mechanisms, or cargo compartments. Such internal organization was incompatible with natural formation through gravitational accretion or collisional assembly and clearly indicated artificial construction. The mass distribution appeared to be optimized for rotational stability and structural integrity under the stresses of interstellar travel and maneuvering operations. This level of engineering optimization suggested design principles that could create structures capable of operating reliably across timescales measured in geological epochs. Particle detector measurements from the CubeSat encounters had detected organized particle flows in 3I Atlas's vicinity that showed characteristics of controlled plasma streams rather than natural solar wind interactions. The particle energies and directional properties indicated acceleration mechanisms that required sophisticated electromagnetic field control systems. The particle streams showed modulation patterns that correlated with radio transmissions and trajectory modifications, suggesting integrated systems that could coordinate multiple operational functions simultaneously. Such coordination required computational capabilities that could manage complex system interactions in real time. The particle emissions appeared to serve multiple functions, including propulsion, communication, and possibly defensive screening against micrometeorite impacts or hostile electromagnetic interference. This multifunctional approach demonstrated engineering efficiency that maximized operational capability while minimizing system complexity and mass requirements. The magnetic field measurements had revealed field structures around 3I Atlas that showed characteristics of actively controlled electromagnetic systems rather than natural magnetization patterns. These fields demonstrated temporal variations that synchronized with other operational activities, indicating integrated electromagnetic management systems. The field configurations appeared to be optimized for multiple simultaneous functions, including charge particle manipulation, electromagnetic shielding, and possibly communication beam steering. Such multifunctional field systems would represent mastery of electromagnetic engineering far beyond current human capabilities. The magnetic field patterns showed evidence of field line manipulation that could control charged particle trajectories with extraordinary precision, potentially explaining how 3I Atlas could generate directional thrust without detectable reaction mass ejection. Such capabilities would represent revolutionary advances in propulsion technology. Chemical analysis of trace materials detected in Earth's vicinity during 3I Atlas's passage had revealed molecular structures that couldn't form through known natural processes. These compounds showed atomic arrangements that appeared to be optimized for specific mechanical electrical or chemical properties rather than representing thermodynamically stable configurations. The synthetic molecules included polymers with properties that exceeded anything achievable with current material science, showing combinations of strength, flexibility, and environmental resistance that would be invaluable for interstellar travel applications. These materials suggested manufacturing capabilities that could design and produce substances with precisely controlled properties. Some detected compounds appeared to be self-assembling or self-repairing materials that could maintain their structural integrity despite damage from cosmic radiation, micrometeorite impacts, or extreme temperature variations. Such adaptive materials would be essential for systems that must operate reliably across interstellar distances and timescales. The morphological analysis of 3I Atlas's surface features had revealed structures that maintained geometric precision despite exposure to the hostile environment of interstellar space. These features showed organizational patterns that suggested systematic maintenance and repair capabilities rather than gradual degradation expected from natural weathering processes. The surface structures appeared to be designed for modularity and serviceability, with component interfaces that would allow replacement or upgrading of individual systems without compromising overall operational integrity. Such design principles indicated engineering approaches optimized for extremely long operational lifetimes. The geometric relationships between different surface features suggested systematic placement according to engineering principles that optimized coverage, redundancy, and operational efficiency. This level of design integration indicated sophisticated system architecture that could coordinate multiple subsystems for maximum overall capability. Spectroscopic monitoring had documented systematic changes in 3I Atlas's emissions that correlated with its distance from the Sun and proximity to major planets, suggesting adaptive systems that could modify their operations based on local environmental conditions. This environmental responsiveness indicated sophisticated sensor systems and autonomous decision-making capabilities. The emission patterns showed evidence of learning behaviors, with response characteristics that evolved over time as the object encountered different environmental conditions. Such adaptive capabilities suggested artificial intelligence systems that could optimize performance based on accumulated experience and environmental feedback. The systematic nature of these behavioral adaptations indicated programming sophistication that could handle complex decision-making processes autonomously without requiring real-time control from distant operators. Such autonomy would be essential for systems operating across interstellar distances, where communication delays measure in years or decades. The energy management systems inferred from thermal and electromagnetic observations had demonstrated capabilities that exceeded anything achievable with known power generation and storage technologies. The object had maintained consistent operational levels throughout its passage, despite varying energy inputs from solar radiation. The power systems appeared to be capable of storing enormous amounts of energy in compact forms while providing stable output for extended periods. Such energy storage capabilities would be essential for interstellar missions that must operate in the energy-poor environment between stellar systems. The efficiency of 3I Atlas's energy utilization suggested power management systems that could optimize energy allocation across multiple competing operational requirements, while maintaining critical system functions under all environmental conditions. This level of power management sophistication would represent major advances in energy technology. The communication systems demonstrated by 3I Atlas had shown capabilities that exceeded human technology in several key areas, including signal processing, error correction, and adaptive modulation. The transmission protocols showed evidence of sophisticated encoding that could maintain information integrity across interstellar distances despite interference and signal degradation. The communication beam steering capabilities suggested antenna systems that could maintain precise targeting accuracy despite the object's complex rotational and translational motions. Such pointing precision would be essential for maintaining communication links across interstellar distances, where small angular errors translate to enormous spatial separations. The data compression algorithms inferred from transmission analysis showed efficiency levels that exceeded current human capabilities, suggesting information processing technologies that could encode maximum information content in minimum transmission bandwidth. Such efficiency would be crucial for communication across the energy-limited environment of interstellar space. The navigation systems inferred from trajectory analysis had demonstrated precision that exceeded human spaceflight capabilities by orders of magnitude. The object had executed course corrections with accuracy that suggested navigation sensors capable of measuring position and velocity with extraordinary precision across interstellar distances. The trajectory optimization demonstrated by 3i Atlas's path through the solar system suggested computational capabilities that could solve complex multi-body gravitational problems in real time while accounting for operational constraints and mission objectives. Such computational power would be essential for autonomous interstellar navigation. The integration of navigation, propulsion, and communication systems demonstrated by 3i Atlas suggested system architecture that could coordinate multiple complex operations simultaneously while maintaining optimal overall mission performance. This level of system integration represented engineering approaches that maximized operational capability within severe mass and energy constraints. The defensive capabilities suggested by 3i Atlas's electromagnetic signatures and particle emissions indicated systems designed to protect against the hazards of interstellar travel, including cosmic radiation, micrometeorite bombardment, and potentially hostile encounters with other technological systems. The electromagnetic shielding capabilities inferred from field measurements suggested systems that could deflect or absorb high-energy particles and electromagnetic radiation that would be lethal to unprotected systems during interstellar transit. Such shielding would be essential for preserving system integrity across journey times measured in millennia. The adaptive defensive responses observed in 3i Atlas's electromagnetic emissions suggested systems that could recognize and respond to different types of threats autonomously, modifying defensive postures based on real-time threat assessment. Such capabilities would be essential for systems operating beyond the range of real-time control from their creators. The manufacturing capabilities suggested by the microscopic particle analysis indicated systems that could produce complex materials and components with atomic-scale precision. Such manufacturing technology would be essential for maintaining and repairing systems during extended interstellar missions where replacement parts must be produced locally. The self-assembly and self-repair capabilities observed in collected particles suggested manufacturing systems that could produce and maintain complex structures autonomously, without requiring external control or intervention. Such capabilities would be essential for systems that must remain operational for geological time periods. The material properties observed in synthetic compounds suggested manufacturing technologies that could design and produce substances with precisely controlled characteristics optimized for specific applications. Such capabilities would represent major advances in materials science and engineering. The sensor capabilities demonstrated by 3i Atlas's systematic information gathering suggested systems that could detect and analyze electromagnetic emissions, gravitational fields, and particle distributions with sensitivity exceeding current human technology. Such sensor capabilities would be essential for comprehensive reconnaissance and scientific investigation. The data processing capabilities inferred from 3i Atlas's behavioral patterns suggested computational systems that could analyze complex information in real time while maintaining multiple concurrent operational functions. Such computational power would be essential for autonomous operation in complex and dynamic environments. The information storage and transmission capabilities demonstrated by 3i Atlas suggested systems that could accumulate, organize, and transmit vast amounts of data across interstellar distances while maintaining information integrity, despite transmission delays and environmental interference. The artificial intelligence capabilities implied by 3i Atlas's adaptive behaviors suggested systems that could learn from experience, make autonomous decisions, and optimize performance without external guidance. Such AI capabilities would be essential for interstellar missions that must operate independently for extended periods. The mission planning capabilities demonstrated by 3i Atlas's systematic survey operations suggested AI systems that could develop and execute complex operational plans while adapting to changing circumstances and opportunities. Such planning capabilities would be essential for maximizing scientific and intelligence gathering during limited duration encounters. The threat assessment and response capabilities suggested by 3i Atlas's defensive behaviors indicated AI systems that could evaluate potential dangers and implement appropriate countermeasures autonomously. Such capabilities would be essential for survival during interstellar missions that might encounter unknown hazards or hostile entities. As the full implications of the 3i Atlas investigation became clear through detailed analysis of the accumulated data, the scientific community found itself grappling with evidence that fundamentally challenged human understanding of what was possible through technological development. The object had demonstrated capabilities that exceeded human technology in virtually every measurable parameter. The engineering principles demonstrated by 3i Atlas suggested technological approaches that could solve problems currently considered intractable by human science and engineering. The integration of multiple advanced technologies into a single system capable of autonomous interstellar operation represented achievements that would require revolutionary advances in multiple fields simultaneously. The mission capabilities demonstrated by 3i Atlas implied civilization-level technological achievements that could support interstellar exploration and possibly colonization on scales that dwarf current human spaceflight capabilities. Such achievements suggested technological civilizations with capabilities and resources far exceeding anything humans had ever contemplated. The intelligence-gathering capabilities demonstrated by 3i Atlas raised profound questions about humanity's exposure to observation and analysis by non-human intelligences. The systematic nature of the object's reconnaissance activities suggested that our technological capabilities, social organization, and potential threat levels had been thoroughly documented and transmitted to unknown recipients. The implications extended far beyond scientific curiosity to encompass fundamental questions about humanity's security, privacy, and future development in a universe that contained intelligences with capabilities far exceeding our own. The evidence suggested that human civilization was being monitored and assessed by entities whose intentions and capabilities remained completely unknown. The technological revolution that would be required to match the capabilities demonstrated by 3i Atlas would fundamentally transform human civilization, potentially solving current limitations in energy, materials, manufacturing, computation, and transportation, while creating entirely new possibilities for human development and expansion. Yet the same technologies that enabled 3i Atlas's impressive capabilities could potentially be used for purposes hostile to human interests, creating unprecedented challenges for defense and security planning in an era where the threats might come from sources with technological advantages measuring in millennia of development. The 3i Atlas investigation had demonstrated that the universe contained active technological civilizations with capabilities that challenged human understanding of what was possible through engineering and scientific development. Whether these civilizations were friendly, indifferent, or potentially hostile remained unknown, but their existence had been definitively established through direct observation and analysis. The hard-to-believe images and data from 3i Atlas represented humanity's first confirmed encounter with advanced non-human technology, marking a watershed moment in human history when we learned definitively that we were not alone in developing the capability to travel between stars and gather intelligence about other civilizations. The evidence had moved far beyond the realm of speculation or wishful thinking into the domain of measurable, reproducible observations that could not be explained through any known natural processes. The scientific community had been forced to acknowledge that the universe contained intelligences capable of achievements that exceeded human technology by orders of magnitude. The investigation had revealed technologies and capabilities that would reshape human understanding of what was possible through scientific and engineering development, while simultaneously raising profound questions about humanity's place in a universe populated by intelligences whose capabilities and intentions remained mysterious. The legacy of 3i Atlas would influence human development for generations, serving as both inspiration for technological advancement and warning about the challenges that might await a species taking its first steps toward becoming an interstellar civilization in a universe already populated by entities with millions of years of technological development. The final analysis of the 3i Atlas data had confirmed what many researchers had suspected, but few had dared to state publicly. We were not alone. We were being watched, and we were being evaluated by intelligences whose capabilities exceeded our own by margins that challenged human comprehension of what technological development could achieve. The hard-to-believe reality was that 3i Atlas had been exactly what the most extraordinary interpretations had suggested, a sophisticated technological system created by non-human intelligence for the purpose of gathering information about human civilization and our solar system. The implications of this confirmation would reverberate through human society for generations to come. The mounting evidence from those final months of observation forced even the most skeptical members of the scientific establishment to confront a reality they had spent careers dismissing as impossible. By April 2026, the comprehensive analysis of 3 Atlas data had reached conclusions that no amount of conventional explanation could rationalize away. The object had not simply been an unusual comet or exotic natural phenomenon, it had been something far more significant, something that redefined humanity's understanding of its place in the cosmic order. The breakthrough came through quantum spectroscopy analysis conducted at the European Southern Observatory's Advanced Instrumentation Facility. Using techniques that pushed the boundaries of molecular detection, researchers identified emission signatures that violated fundamental principles of natural chemistry. The spectral lines showed isotopic ratios that could only be produced through controlled nuclear synthesis, processes that required technological capabilities far exceeding anything achieved by human civilization. Dr. Elena Vasquez, the lead spectroscopist on the international analysis team, described the findings as categorically inconsistent with any known stellar nucleosynthesis process. The isotopic signatures detected in 3I Atlas's emissions included artificially enhanced concentrations of elements that simply don't occur naturally in the abundances observed. These weren't trace contaminations or measurement errors. They were substantial quantities of materials that could only be produced through deliberate nuclear engineering. The implications were staggering because isotopic composition serves as an immutable fingerprint of natural processes. Stars create elements through well-understood nuclear reactions that produce predictable isotope ratios. Cosmic ray bombardment, radioactive decay, and interstellar chemical processing all follow established patterns that have been verified through decades of observation. 3I Atlas violated these patterns in ways that demanded technological explanations. Laboratory analysis of the microscopic debris particles collected during 3I Atlas's passage revealed structures that pushed the boundaries of what current materials science considered possible. Electron microscopy showed atomic-scale architecture that appeared deliberately engineered rather than naturally formed. The particles contained layered arrangements of elements that had been precisely positioned to create materials with properties that exceeded anything achievable through natural crystal formation processes. The manufacturing precision observed in these microscopic samples suggested fabrication techniques that could manipulate matter at the individual atomic level. Some particles showed internal structures that resembled miniature machines, with components arranged in functional configurations that implied specific operational purposes. The level of engineering sophistication was comparable to theoretical concepts in advanced nanotechnology, but implemented with precision that exceeded current human capabilities by orders of magnitude. Chemical analysis revealed synthetic polymers within the particle samples that combined mechanical strength, electrical conductivity, and self-repair capabilities in ways that defied conventional materials engineering. These substances appeared to be designed for extreme durability under the harsh conditions of interstellar space, including resistance to cosmic radiation, temperature fluctuations, and micrometeorite bombardment that would destroy conventional materials over extended time periods. The electromagnetic emissions detected throughout 3 Atlas's passage had been subjected to advanced signal processing analysis using techniques originally developed for deep space communication systems. The results revealed data structures embedded within what had initially appeared to be random radio noise. These weren't the chaotic electromagnetic phenomena expected from natural plasma processes, but organized information streams that followed sophisticated communication protocols. The signal analysis revealed error correction algorithms, data compression schemes, and channel management techniques that demonstrated information processing capabilities far exceeding current human technology. The transmission protocols showed evidence of adaptive modulation that could optimize signal clarity and information density based on changing transmission conditions. Such capabilities would be essential for reliable communication across interstellar distances where signal degradation and interference present enormous challenges. Most significantly, the data streams appeared to contain systematic catalogues of information about Earth's electromagnetic signature, orbital mechanics, and the technical specifications of human observational equipment. The level of detail suggested that 3I Atlas had been conducting comprehensive reconnaissance of human technological capabilities throughout its passage through the inner solar system. The trajectory analysis had revealed the full scope of 3 Atlas's maneuvering capabilities during its solar system transit. High-precision astrometric measurements from observatories worldwide showed that the object had executed dozens of subtle course corrections that collectively altered its departure trajectory by several degrees. These weren't random perturbations caused by outgassing or thermal effects, but deliberate navigational adjustments that appeared designed to optimize observational opportunities. The energy requirements for these maneuvers exceeded what could be provided by any known chemical propulsion system. Computer modeling suggested that the observed trajectory modifications would require either exotic propulsion technologies that could manipulate gravitational fields directly, or energy storage capabilities that defied conventional physics. The efficiency of the course corrections implied propulsion systems that could generate thrust without detectable reaction mass ejection. The navigational precision demonstrated by these maneuvers suggested guidance systems capable of measuring position and velocity with extraordinary accuracy across interstellar distances. The trajectory optimization implied computational capabilities that could solve complex multi-body gravitational problems in real time while accounting for mission objectives and operational constraints that remained unknown to human observers. Thermal analysis of 3 I-Atlas's infrared emissions revealed temperature management systems that operated with technological sophistication, far exceeding natural thermal regulation. The object maintained precise temperature distributions across its surface despite varying solar illumination angles and distances, suggesting active heat management systems that could redistribute thermal energy with extraordinary precision. The temperature gradients detected by space-based infrared observatories showed discrete thermal zones that remained stable over observation periods spanning months. This level of thermal control was incompatible with natural materials responding passively to solar heating, and clearly indicated sophisticated thermal management systems designed to maintain optimal operating conditions for internal components. The thermal signatures suggested internal heat sources that operated independently of solar energy input, maintaining consistent power levels throughout 3 I-Atlas's passage despite the inverse square relationship between distance and solar radiation intensity. Such energy independence would be essential for interstellar missions that must operate in the energy-poor environment between stellar systems for extended periods. Magnetic field measurements obtained during close spacecraft encounters revealed organized electromagnetic structures that resembled the field patterns generated by advanced technological systems rather than natural magnetization of rocky materials. These fields showed temporal variations that correlated perfectly with radio transmissions and trajectory modifications, suggesting integrated electromagnetic systems that coordinated multiple operational functions. The magnetic field configurations appeared designed to serve multiple simultaneous purposes, including charged particle manipulation, electromagnetic shielding, and communication beam steering. The field patterns showed evidence of active control systems that could modify magnetic field geometry in real time to optimize performance for different operational requirements. The electromagnetic field structures suggested mastery of magnetic confinement technologies that could control charged particle flows with extraordinary precision. Such capabilities might explain how 3 I-Atlas could generate directional thrust without detectable reaction mass, representing revolutionary advances in propulsion physics that challenge fundamental assumptions about momentum conservation. Radio astronomy facilities had detected increasingly sophisticated emission patterns throughout 3 Atlas's visible passage that showed characteristics resembling advanced communication systems rather than natural electromagnetic phenomena. The signals exhibited modulation schemes, frequency management, and transmission timing that followed protocols designed for efficient information transfer across vast distances. Very long baseline interferometry networks achieved sufficient angular resolution to map the source regions of radio emissions within 3 Atlas's immediate vicinity. The resulting maps revealed antenna-like structures that maintained consistent orientations and operational characteristics despite the chaotic environment of the surrounding gas and dust emissions. These structures appeared to be engineered systems rather than natural formations. The radio emissions showed evidence of adaptive communication protocols that could modify transmission parameters based on changing geometric relationships with potential receivers. The system demonstrated capabilities for automatic frequency selection, power optimization, and beam steering that would be essential for maintaining communication links across interstellar distances with mobile platforms. Surface topology analysis based on high-resolution radar observations revealed features that maintain geometric precision across 3I Atlas's entire observable surface. These structures showed organizational patterns and systematic placement that suggested engineering design principles rather than random formation through natural processes like impact cratering or thermal cycling. The surface features included what appeared to be access ports, sensor arrays, and communication systems arranged in configurations that maximized operational coverage and efficiency. The geometric relationships between different surface elements suggested systematic engineering that optimized multiple operational requirements simultaneously, while maintaining structural integrity under the stresses of interstellar travel. Radar reflectivity measurements showed surface characteristics that were inconsistent with natural rocky or icy compositions. The reflection patterns suggested materials with controlled electromagnetic properties that had been engineered for specific operational requirements rather than formed through natural geological or cosmic processes. Gravitational field mapping conducted during spacecraft flyby encounters revealed mass distribution patterns within 3I Atlas that were incompatible with natural object formation through gravitational accretion or collisional assembly. The internal mass distribution showed organized structures that suggested deliberate placement of dense materials to optimize rotational stability and structural integrity. The gravitational measurements indicated hollow regions within the object that could accommodate internal systems, propulsion mechanisms, or information storage facilities. Such internal organization clearly indicated artificial construction rather than natural formation processes that would produce random density variations throughout the object's interior. The mass distribution appeared optimized for operational efficiency during extended interstellar missions, with structural characteristics that could maintain integrity under the mechanical stresses of acceleration, deceleration, and maneuvering operations across journey times measured in millennia. Particle detection systems aboard close-approach spacecraft measured charged particle flows in 3I Atlas's vicinity that showed characteristics of controlled plasma streams rather than natural interactions with solar wind. The particle energies and directional properties indicated electromagnetic acceleration systems that could manipulate charged matter with extraordinary precision. The particle emissions appeared to serve multiple operational functions simultaneously, including propulsion thrust generation, electromagnetic field maintenance, and possibly defensive screening against micrometeorite impacts or hostile electromagnetic interference. This multifunctional approach demonstrated engineering efficiency that maximized operational capability while minimizing system complexity and mass requirements. The particle stream characteristics showed modulation patterns that correlated with radio transmissions, trajectory modifications, and thermal management operations, indicating integrated control systems that could coordinate multiple subsystems for optimal overall performance. Such coordination required computational capabilities that exceeded current human technology by substantial margins. Spectroscopic monitoring throughout 3I Atlas's passage documented systematic changes in molecular emissions that appeared to be controlled responses to environmental conditions rather than passive reactions to solar heating. The emission patterns showed evidence of adaptive systems that could modify operational parameters based on real-time environmental assessment and mission requirements. The molecular emission signatures showed temporal variations that followed patterns resembling learning algorithms, with response characteristics that evolved over time as the object encountered different environmental conditions. Such adaptive capabilities suggested artificial intelligence systems that could optimize performance based on accumulated experience and environmental feedback. The systematic nature of these behavioral adaptations indicated programming sophistication that could handle complex decision-making processes autonomously without requiring real-time control from distant operators. Such autonomy would be essential for systems operating across interstellar distances where communication delays measure in years or decades. Polarimetric analysis of scattered light from 3I Atlas revealed optical properties that were fundamentally inconsistent with any known natural materials. The polarization characteristics suggested surface treatments or coatings that had been engineered for specific electromagnetic interaction properties, rather than the random optical variations expected from natural rock or ice formations. The optical signatures indicated materials that could maintain their engineered characteristics despite prolonged exposure to cosmic radiation, solar heating, and micrometeorite bombardment during interstellar transit. Such durability suggested synthetic materials with properties that exceeded anything achievable with current human materials science and manufacturing technology. The temporal stability of optical properties over observation periods spanning months demonstrated materials engineering that could create substances capable of maintaining precise operational characteristics throughout extended exposure to the hostile environment of space. Such capabilities would be essential for systems designed to operate reliably across geological timescales. Chemical analysis of trace atmospheric contamination detected during 3I Atlas's Earth approach revealed molecular species that couldn't form through any known natural chemical processes. The detected compounds included complex hydrocarbons, metallic oxides, and synthetic polymers that indicated industrial processing rather than the primitive chemistry expected from interstellar ice and dust. The synthetic molecules showed atomic arrangements that appeared optimized for specific mechanical, electrical, or chemical properties, rather than representing thermodynamically stable configurations that would result from natural chemical evolution. These materials suggested manufacturing capabilities that could design and produce substances with precisely controlled characteristics. Some detected compounds appeared to incorporate self-assembling or self-repairing molecular architectures that could maintain structural integrity despite damage from radiation, thermal cycling, or physical impact. Such adaptive materials would be invaluable for systems that must maintain operational capability throughout extended interstellar missions lasting thousands of years. Energy system analysis based on thermal emissions and electromagnetic signatures suggested power generation and management capabilities that exceeded current human technology in several fundamental areas. 3I Atlas maintained consistent operational energy levels throughout its solar system passage, despite dramatic variations in available solar energy as distance from the Sun changed. The power systems appeared capable of storing enormous amounts of energy in compact configurations, while providing stable output for extended periods without degradation. Such energy storage technologies would be essential for interstellar missions that must operate in energy-poor environments between stellar systems for extended periods. The efficiency of energy utilization suggested power management systems that could optimize energy allocation across multiple competing operational requirements while maintaining critical system functions under all environmental conditions. This level of energy management represented major advances beyond current human capabilities in power generation, storage, and distribution. Communication system analysis revealed capabilities that exceeded human technology in signal processing, error correction, and adaptive transmission protocols. The communication systems demonstrated by 3I Atlas could maintain information integrity across interstellar distances despite signal degradation, interference, and the enormous time delays inherent in interstellar communication. The transmission beam steering capabilities suggested antenna systems that could maintain precise targeting accuracy despite complex rotational and translational motions throughout interstellar flight. Such pointing precision would be essential for maintaining communication links across distances where small angular errors translate to enormous spatial separations at the receiver. The data encoding efficiency inferred from transmission analysis exceeded current human information processing capabilities, suggesting compression algorithms that could encode maximum information content in minimum transmission bandwidth. Such efficiency would be crucial for communication across the bandwidth-limited and energy-constrained environment of interstellar space. Manufacturing capability analysis based on microscopic particle examination suggested production systems that could create complex materials and components with atomic-scale precision. The observed manufacturing precision would be essential for producing and maintaining sophisticated systems during extended interstellar missions where replacement components must be fabricated locally using available materials. The self-assembly and self-repair capabilities observed in collected particle samples indicated manufacturing systems that could produce and maintain complex structures autonomously without external control or intervention. Such capabilities would be essential for systems that must remain operational for geological time periods without access to external maintenance or repair facilities. The material properties observed in synthetic compounds suggested manufacturing technologies that could design and produce substances with characteristics precisely optimized for specific operational requirements. Such capabilities represented revolutionary advances in materials science that could solve currently intractable engineering problems in extreme environment applications. Sensor system capabilities inferred from 3 iAtlas's systematic information gathering operations suggested detection and analysis systems with sensitivity and resolution exceeding current human sensor technology. The reconnaissance capabilities demonstrated during the solar system passage indicated sensor systems that could detect and analyze electromagnetic emissions, gravitational fields, and particle distributions with extraordinary precision. The data processing capabilities required to analyze and catalog the vast amounts of information gathered during 3 iAtlas's passage suggested computational systems with processing power that exceeded current human-computer technology by orders of magnitude. Such computational capabilities would be essential for real-time analysis of complex environmental data during autonomous interstellar operations. The information storage and retrieval systems implied by 3 iAtlas's systematic data collection suggested memory technologies that could store vast amounts of information in compact, durable formats while maintaining data integrity throughout extended interstellar missions. Such storage capabilities would be essential for accumulating and preserving scientific and intelligence data across journey times measuring in millennia. Artificial intelligence analysis based on 3 iAtlas's adaptive behavior suggested computational systems that could learn from experience, make autonomous decisions, and optimize performance without external guidance. The AI capabilities demonstrated during the solar system passage exceeded current human artificial intelligence in autonomous operation, environmental adaptation, and mission planning. The mission execution capabilities demonstrated by 3 iAtlas's systematic survey operations suggested AI systems that could develop and implement complex operational plans while adapting to changing circumstances and unexpected opportunities. Such planning capabilities would be essential for maximizing scientific return during limited-duration encounters with target systems. The threat assessment and defensive response capabilities suggested by 3 iAtlas's electromagnetic and particle emission patterns indicated AI systems that could evaluate potential dangers and implement appropriate countermeasures autonomously. Such capabilities would be essential for survival during interstellar missions that might encounter unknown environmental hazards or potentially hostile technological systems. Integration analysis of all observed systems suggested engineering approaches that could coordinate multiple advanced technologies into unified operational platforms capable of autonomous interstellar missions lasting thousands of years. The level of system integration demonstrated by 3 iAtlas represented engineering achievements that would require revolutionary advances in multiple technological fields simultaneously. The mission architecture implied by 3 iAtlas's capabilities suggested technological civilizations with resources and manufacturing capabilities that could support interstellar exploration programs on scales that dwarf current human space exploration efforts. Such achievements indicated technological development that had progressed far beyond anything humans had achieved or currently contemplated. The intelligence-gathering focus of 3 iAtlas's mission suggested systematic programs for surveying and cataloguing technological civilizations throughout the galaxy. The comprehensive nature of the reconnaissance activities implied that human civilization had been thoroughly analyzed and documented for transmission to unknown recipients with capabilities and intentions that remained completely mysterious. By late 2026, the accumulated evidence from the 3 iAtlas investigation had reached a threshold where even the most conservative scientific institutions could no longer maintain that natural explanations remained viable. The combination of artificial isotopes, engineered materials, controlled electromagnetic emissions, systematic trajectory modifications, and integrated technological systems created an overwhelming case for artificial origin that transcended reasonable scientific skepticism. International scientific organizations convened emergency protocols for handling discoveries that fundamentally challenged basic assumptions about natural phenomena and humanity's place in the universe. The 3 iAtlas investigation had demonstrated that existing frameworks for evaluating unusual observations were inadequate when dealing with evidence of advanced non-human technology operating within our solar system. The evidence speaks for itself, and what it's telling us should fundamentally change how we view our place in the universe. 3 iAtlas wasn't just an unusual comet or an extreme example of natural phenomena. It was a sophisticated technological system, engineered by non-human intelligence, conducting systematic reconnaissance of human civilization and our solar system. The isotopic signatures, manufactured materials, controlled maneuvers, and organised communication protocols paint an undeniable picture that we are not alone, and we are being watched by intelligences whose capabilities exceed our own, by margins that challenge human comprehension of technological possibility.